Greenland stretches as an endless frozen expanse, its ice hiding secrets that scientists cannot explain. Strange phenomena have emerged: lakes that vanish overnight, glaciers that rumble without warning, and ice stained crimson as if bleeding from some unseen force. Each anomaly hints at processes beneath the surface that challenge conventional understanding and defy expectation. As these mysteries unfold, you will traverse deep crevasses and follow subglacial rivers, witnessing fleeting traces of life, movement, and change within the ice. From sudden meltwater tunnels to the eerie blood snow, every discovery draws you into Greenland's enigmatic rhythms, revealing a frozen world that conceals more than it reveals and inviting you to confront the unknown at the edge of the ice. The sudden draining of Greenland's hidden lakes. Far from the scattered coastal settlements of Greenland, the centre of the island is buried beneath a frozen landscape so vast that it can conceal entire geological systems from direct observation. The ice sheet stretches for thousands of kilometres, its surface appearing silent and immobile from above, yet modern instruments have revealed a world of movement hidden beneath that frozen skin. Among the most baffling discoveries are enormous bodies of water trapped within and beneath the ice itself. These hidden reservoirs can remain sealed for years or even decades, slowly filling as meltwater trickles through fractures and channels deep inside the glacier. Then, without warning, the lakes vanish, draining in a matter of hours through pathways scientists cannot directly see. The discovery of these hidden lakes did not come from explorers standing on the ice, but from satellites and airborne radar scanning the surface from far above. During the early 21st century, glaciologists began noticing sudden changes in the elevation of the ice sheet. Sections of the surface would rise gradually over months, forming subtle domes across several square kilometres before abruptly collapsing. Such changes were far too large to be caused by ordinary snowfall or seasonal melting. When scientists compared repeated measurements taken by laser altimeters aboard orbiting satellites, the pattern became clear. Beneath those swelling patches of ice, lakes of meltwater were quietly collecting until something triggered their sudden release. The idea that water could pool beneath miles of ice once seemed unlikely, but Greenland's ice sheet is far from solid. During the summer months, sunlight melts vast quantities of snow at the surface, forming rivers that snake across the glacier in brilliant blue channels. Some of this water drains into deep shafts known as moulins, vertical tunnels that plunge through the ice and carry meltwater downward. As the water descends, it can encounter layers of denser ice or sediment that trap it temporarily, allowing entire lakes to accumulate far below the surface where temperatures remain close to freezing. One of the most striking examples of this phenomenon was recorded in western Greenland in 2006, when satellite imagery revealed that a large lake resting on the ice sheet suddenly disappeared in less than a day. Researchers later estimated that more than 40 million cubic meters of water drained through the glacier during that single event. The volume was comparable to the water held in thousands of Olympic swimming pools, yet it vanished without leaving an obvious outlet on the surface. Instead, the water forced open fractures in the ice, plunging downward toward the bedrock beneath the glacier. To understand what was happening, scientists deployed GPS receivers, radar instruments, and seismometers across sections of the ice sheet where hidden lakes were suspected to form. These instruments revealed that when a lake drains, the entire glacier can briefly shift in response. The sudden surge of water at the base of the ice reduces friction between the glacier and the rock beneath it, allowing the massive sheet of ice to slide forward slightly. Some instruments have recorded movement of several meters within a single day, a remarkable acceleration for a structure that normally creeps forward only gradually over time. Yet the deeper mystery lies in the pathways the water follows once it begins to drain. The base of the Greenland ice sheet is an uneven world of rock ridges, sediment layers, and channels carved by ancient glaciers. Water moving through this environment can carve new routes through the ice, or exploit existing cracks that extend for kilometers. Radar surveys have revealed complex networks of subglacial rivers beneath the ice sheet, but mapping them precisely remains extremely difficult because the ice above can be more than 3 kilometers thick. Evidence suggests that these drainage events may occur more frequently than scientists once realized. Satellite measurements collected over the past 2 decades have identified dozens of locations where the ice surface has risen and collapsed in patterns consistent with hidden lakes forming and emptying. In some regions, the same area appears to fill repeatedly before draining again years later. The process resembles a slow, unseen heartbeat within the glacier, with water accumulating quietly until the pressure becomes strong enough to force an escape. The implications extend far beyond the lakes themselves. When water suddenly rushes beneath the ice sheet, it can alter the speed at which glaciers move toward the ocean. Faster glacier flow increases the rate at which ice is delivered to coastal fjords, where it eventually breaks away as icebergs. Some researchers believe that repeated drainage events may help explain why certain glaciers in western Greenland occasionally accelerate in ways that are difficult to predict using existing models. One of the glaciers most closely monitored in this region is Jakobshavn Glacier, a fast-moving outlet glacier that drains a large portion of the ice sheet toward the sea. Instruments placed on the surrounding ice have recorded sudden movements that coincide with the timing of meltwater drainage events inland. Although the relationship between hidden lakes and glacier motion is still being investigated, the evidence suggests that water moving beneath the ice can influence the stability of glaciers many kilometers away. Understanding these hidden drainage systems is challenging because the events occur far beneath the surface and often without visible warning. Researchers rely heavily on satellite altimetry, radar imaging, and computer models to reconstruct what happens when a lake drains. Even with these tools, the exact triggers remain uncertain. Some lakes may burst when pressure within the water becomes strong enough to fracture the ice above it. Others may connect to existing channels beneath the glacier, allowing water to escape suddenly once the path opens. The extreme environment adds further complications. Temperatures across Greenland's interior can remain far below freezing for most of the year, yet water still moves through this glacier because the immense pressure of the overlying ice lowers the melting point at the base. This creates a delicate balance where liquid water, solid ice, and shifting sediments interact in ways that are difficult to reproduce in laboratory experiments. As a result, many aspects of subglacial hydrology remain poorly understood despite decades of research. Even as satellites continue to monitor the ice sheet with increasing precision, the hidden lakes of Greenland remain largely invisible except for the brief surface changes that reveal their presence. Scientists know they exist, they can measure the sudden collapses that mark their disappearance, and they can estimate the astonishing volumes of water involved, yet the exact routes that carry that water through the depths of the glacier remain concealed beneath kilometers of ice. And somewhere beneath that silent white landscape, another unseen lake may already be filling, waiting for the moment when the pressure becomes too great for the ice above it to hold. The darkening ice mystery. Glaciologists studying satellite measurements of the Arctic began noticing a puzzling trend in data, tracking the reflectivity of ice surfaces, a change subtle enough to escape immediate attention, yet persistent enough to raise concern among researchers examining the long-term condition of the ice sheet. Over time, those measurements suggested that parts of the frozen expanse covering Greenland were gradually losing their brightness. At first, the difference seemed minor, almost statistical, the kind of variation that might appear naturally across such a vast landscape. But as the records accumulated across years of observation, the signal became difficult to dismiss. Something across the ice sheet was slowly altering the way sunlight interacted with the frozen surface. Spaceborne instruments designed to monitor Earth's changing climate soon confirmed that the pattern was not confined to a single region. Satellite sensors measuring surface reflectivity, known to scientists as albedo, began revealing broad areas where the ice sheet was absorbing more solar energy than earlier measurements suggested it should. These observations did not point to sudden melting events or dramatic fractures in the glacier, but to something quieter and more gradual. Patches of darker ice appeared scattered across the otherwise brilliant white surface, sometimes extending across several kilometers, sometimes forming irregular streaks that followed the subtle contours of the glacier itself. The significance of this shift becomes clearer when considering how polar ice normally behaves under sunlight. Fresh snow and clean glacial ice reflect a remarkable portion of incoming solar radiation, sending much of that energy back into the atmosphere and helping regulate the temperature of polar environments. This reflective quality is one of the reasons the Arctic has long functioned as a stabilizing component of Earth's climate system. When the surface darkens, even slightly, that balance begins to change. Darker surfaces absorb more sunlight, converting it into heat, and that heat accelerates the melting of the surrounding ice in ways that can reshape the landscape. researchers working directly on the ice sheet have encountered the phenomenon during summer expeditions across Greenland's interior. Travelling across the glacier by snowmobile or helicopter, field teams have occasionally arrived at stretches where the familiar brilliance of the ice gives way to a muted surface marked by grey, brown, or even blackened tones. These areas do not resemble the dramatic fractures or meltwater lakes often associated with glacial change. Instead, they appear as quiet discolorations spreading across the ice like shadows, sometimes visible only when the sunlight strikes the surface at certain angles. One of the earliest explanations scientists explored involved the possibility of dust settling across the ice sheet. Strong winds moving across continents can lift fine mineral particles into the atmosphere, carrying them across oceans before eventually depositing them on distant landscapes. Greenland's ice sheet is not isolated from these global atmospheric pathways. Dust originating from exposed soils or deserts thousands of kilometers away can travel into the Arctic, settling gently across the snow. Even small amounts of mineral dust can reduce the reflectivity of ice, allowing it to absorb more sunlight. Another factor entered the discussion when atmospheric researchers began studying the presence of black carbon in Arctic snow. Black carbon consists of microscopic particles produced during the incomplete combustion of fossil fuels, wood, or other organic materials. These particles are light enough to drift through the atmosphere for long periods, sometimes travelling vast distances before falling to the ground. When black carbon settles on snow or ice, it creates tiny dark specks that absorb sunlight. Laboratory studies have shown that even very small concentrations can reduce the reflective properties of snow surfaces. Yet measurements collected from many darkened areas suggested that neither dust nor soot alone could fully explain the changes researchers were observing. In some places, the darkening seemed too widespread or too intense to be caused solely by atmospheric particles. This realization led scientists to begin examining samples taken directly from the ice itself. What they found under microscopes revealed an unexpected dimension to the mystery. The darkened ice was not simply coated with mineral grains or pollution. In many cases, it was alive. Microscopic organisms known as ice algae inhabit the uppermost layers of glacial ice, thriving in thin films of meltwater that form during the Arctic summer. These algae contain pigments that protect them from intense sunlight while allowing them to harvest energy through photosynthesis. The pigments also darken the ice surrounding them, turning what might otherwise be a bright surface into a slightly darker shade. Under favourable conditions, these microorganisms can multiply rapidly, forming dense communities that spread across large areas of the glacier. Researchers studying these algae have discovered that their presence can dramatically influence how sunlight interacts with the ice sheet. As the algae grow, they darken the surface and cause it to absorb more heat. That additional heat produces more meltwater, which in turn creates conditions that allow the algae to expand even further. The process forms a feedback loop in which biological activity and melting reinforce one another. What began as a microscopic community becomes a visible transformation of the glacier's surface. As satellite records have continued to accumulate, scientists have realized that the darkening phenomenon likely arises from several processes acting together. Dust carried by wind, soot drifting from distant combustion sources, and the growth of ice algae may all contribute to the changing appearance of the ice sheet. Seasonal melting can also expose older layers of ice that contain trapped impurities, further reducing reflectivity. Untangling the influence of each factor remains difficult because conditions across the ice sheet change constantly with shifting weather patterns and snowfall. Despite advances in remote sensing and field research, predicting where darkening will occur remains a significant challenge. Satellite instruments can detect changes in surface brightness, but they cannot easily determine the precise mixture of dust, biological growth, and meltwater responsible for those changes. Field studies provide detailed measurements, but are limited to small regions of an enormous ice sheet that covers more than 1 million square kilometers. As a result, many questions remain unanswered about how widespread the phenomenon may become in the future. What makes the situation particularly intriguing for researchers is that the ice sheet's changing colour represents more than a simple visual curiosity. The darkening surface alters how the glacier interacts with sunlight, heat, and melting processes, potentially influencing the long-term stability of Greenland's frozen interior. Scientists now recognise that the surface of the ice sheet is far more dynamic than once believed. shaped not only by climate and weather but also by microscopic life and particles carried across the atmosphere. Somewhere across the vast frozen plateau of Greenland, another darkened patch may already be forming, quietly absorbing sunlight while scientists continue searching for a complete explanation. The strange ice earthquakes beneath the glacier. Seismic monitoring stations around the globe first picked up the anomaly in data streaming from Greenland, signals that at first glance resembled ordinary earthquakes but defied conventional explanation. The tremors originated not along tectonic fault lines, but from deep beneath the ice sheet itself, suggesting that the frozen mass of Greenland was generating seismic activity of its own. Researchers initially questioned whether instrumentation errors or distant geological events had caused the readings, but repeated patterns soon made clear that the vibrations were real and uniquely connected to the movement of the glaciers. Something within the ice was shifting with enough force to send measurable waves through the Earth's crust. Some of the pulses appeared almost rhythmic, as if the glacier were operating according to a hidden internal cycle that no one has yet mapped. Closer examination of the data revealed that the seismic signals exhibited a peculiar signature. The energy was distributed differently from tectonic earthquakes, and the timing often coincided with periods of rapid glacier motion. Unlike conventional earthquakes, which typically release accumulated stress along rock faults, these tremors occurred when large portions of ice either surged forward or fractured abruptly. Researchers began to categorize them as a new type of event, now commonly referred to in scientific literature as glacial earthquakes, a phenomenon previously unanticipated in the study of Greenland's frozen interior. In some cases, multiple tremors would follow in quick succession, travelling through the ice like echoes of a hidden subterranean rumble that seemed to anticipate the next movement. The strength of these ice-generated tremors astonished seismologists. Some events were powerful enough to be detected thousands of kilometers away by seismic stations designed to record tectonic activity around the globe. The waves produced by the ice often displayed low-frequency characteristics, indicating that the force responsible originated from a massive mass moving relatively slowly, yet with enough momentum to propagate through the planet's crust. The idea that slowly flowing ice could generate seismic energy on such a scale challenged conventional understanding of both glaciology and seismology. Certain tremors have left researchers puzzled because they appear to originate from regions deep within the ice, where no surface movement has yet been observed. Investigating the mechanisms behind these vibrations revealed that many of these events occur during sudden glacial surges or when massive ice fronts fracture. As glaciers advance, enormous blocks of ice periodically shift or break away, producing energy that travels through the surrounding ice and bedrock. These movements are not continuous but occur in bursts, often during seasonal transitions, when meltwater lubricates the base of the ice, or when internal stresses exceed the strength of the frozen mass. Each tremor acts as a pulse from within the glacier, carrying with it clues about processes deep beneath the surface. Some tremors are accompanied by subtle shifts at the surface that are so brief and faint they're almost imperceptible, leaving scientists to wonder what else is occurring entirely out of view. Several of the strongest glacial earthquakes have been traced to Greenland's fastest-moving outlet glaciers. Among them, Jakobshavn Glacier stands out for its remarkable speed and capacity for iceberg carving. As the glacier channels ice from the interior toward the ocean, it periodically releases enormous chunks into the sea, each carving event capable of generating seismic waves measurable across the region. Scientists have observed that some of the largest recorded tremors coincide precisely with these carving events, highlighting the powerful connection between ice movement and seismic activity. Beyond carving, other sources of glacial tremors have emerged. Collisions between massive ice blocks, sudden internal collapses, and shifts along the glacier bed can all produce measurable vibrations. Each type of movement contributes to a complex and dynamic seismic landscape hidden beneath the ice sheet. The glacier, once thought to be a largely inert frozen mass, is revealed as an active system of energy and motion, where even seemingly subtle adjustments can create waves that ripple through kilometers of ice and rock. To better understand these events, researchers began deploying seismometers directly on the ice sheet. These instruments capture the nuanced vibrations produced by glacial movement, allowing scientists to differentiate between carving, basal sliding, and smaller internal shifts. Data from these sensors has provided unprecedented insight into the glacier's behaviour, revealing that beneath the silent surface, the ice is constantly adjusting, shifting and releasing energy in ways that had previously gone unnoticed. The recordings show that the glacier's motion is far from uniform. Ice flows gradually from Greenland's interior toward the coast, but this flow can accelerate in bursts, producing sudden tremors as ice adjusts to changes in pressure or responds to meltwater lubrication at its base. Even when there is no calving at the terminus, internal stresses can cause ice to fracture or slip along underlying sediment layers, generating low-frequency vibrations that travel vast distances. Long-term monitoring has also revealed a concerning trend. The frequency of glacial earthquakes has increased over the past several decades. Scientists suggest that faster glacier movement, increased iceberg calving, and changing subglacial conditions may all contribute to this uptick. Despite these insights, the precise triggers for many glacial tremors remain unclear, and the potential long-term effects on ice sheet stability are still being studied. Each new recording only deepens the mystery, showing that the glacier is far more dynamic than previously imagined. Some events defy all current models, appearing without warning in areas previously considered geologically quiet, hinting at processes deep within the ice that remain invisible and unexplained. Predicting when these tremors will occur remains extremely challenging. The harsh remote environment of Greenland makes installing and maintaining instrumentation difficult, and many processes occur far beneath the ice where direct observation is impossible. While satellites and seismometers provide data about the glacier's movement and its seismic activity, much of what drives these events remains hidden. Each tremor serves as a reminder that even the most advanced scientific tools can only reveal a fraction of the glacier's inner workings. The glacier seems to harbour a network of stresses and fractures that operate independently of the surface, like a silent orchestra playing notes that no human has yet fully learned to interpret. Taken together, the evidence paints a picture of Greenland's ice sheet as a vast living structure capable of producing seismic energy that echoes across the planet. The glacier's movements are subtle, sudden, and sometimes violent, yet they remain largely invisible to the naked eye. Even as researchers piece together these patterns, the full scope of forces shaping the glacier beneath the frozen surface remains one of the most intriguing mysteries in Arctic science. Beneath Greenland's immense ice sheet, the glacier continues to release sudden tremors that travel through the Earth, hinting at powerful movements unfolding far below the frozen surface, where no instrument can yet fully reveal what is happening. The growing network of hidden subglacial rivers. Radar surveys have begun to reveal traces of liquid water, carving channels beneath Greenland's glaciers, suggesting a hidden network that defies earlier assumptions about how ice sheets behave. Scientists first noticed irregular reflections in ice-penetrating radar data, patterns that did not correspond to the familiar layering of ice or bedrock. Initially dismissed as anomalies or interference, repeated scans confirmed that these signatures represented flowing water beneath kilometers of frozen surface. The discovery hinted at an unseen system quietly routing meltwater under the ice, one that could alter our understanding of glacier dynamics and the hidden architecture of Greenland's frozen interior. Airborne ice-penetrating radar scans show sinuous passages where meltwater collects and moves, weaving through the ice in patterns that scientists are only beginning to interpret. Some channels appear nearly continuous for tens of kilometers, twisting and turning in unexpected directions. Others terminate abruptly, disappearing into subglacial cavities or connecting with hidden lakes. The imagery suggests that these rivers do not follow predictable paths. Instead, their routes are shaped by a combination of ice pressure, underlying geology, and water flow that has remained invisible to researchers until modern radar allowed these glimpses. The scale of these subglacial rivers is staggering, stretching for tens of kilometers and linking numerous lakes, forming a complex system entirely invisible from the surface. Where once scientists imagined isolated pockets of water beneath the ice, it now appears that Greenland may host an extensive circulatory network, moving liquid water across vast distances. Some of these rivers are comparable in size to medium terrestrial rivers, carrying enormous volumes of water under immense pressure, entirely hidden beneath a sheet of ice that can be over 2 kilometers thick. This discovery transforms the perception of the ice sheet from a static, frozen mass to a dynamic, interconnected system. Seasonal changes appear to breathe life into the network, with summer meltwater suddenly surging through channels that had lain dormant beneath the frozen surface. Warm surface meltwater percolates through crevasses and moulins, finding new conduits and occasionally triggering bursts of flow in previously dormant channels. These pulses can cause subglacial lakes to rise and fall dramatically, sometimes draining rapidly in ways that researchers only detect through subtle shifts in ice elevation or sudden movement recorded by GPS instruments. The rivers themselves act like living arteries, responding to environmental conditions far above the glacier. Despite advances in mapping technology, visualizing these rivers remains a formidable challenge, as even radar and satellite measurements can only suggest their full labyrinthine complexity. The resolution of airborne radar allows researchers to detect the presence of water, but not always its precise depth, velocity, or chemical composition. Modelling efforts must fill in the gaps, relying on physical principles of ice flow and hydrology to infer the hidden connections between lakes and channels. Even with these sophisticated tools, every new survey reveals surprises, emphasizing that the ice conceals far more than can be observed directly. Some hidden pathways twist and curve in unexpected directions, navigating around bedrock formations and ice ridges as if guided by forces scientists cannot yet fully explain. Channels sometimes bend sharply, join with others, or split into multiple smaller streams, creating a complex branching network that defies simple categorization. In certain regions, rivers appear to intersect subglacial ridges and depressions in ways that suggest water is exploiting weaknesses in the ice sheet itself. These patterns imply that the ice is far from passive, dynamically responding to the presence and pressure of flowing water over timescales that can range from hours to decades. Research has shown that the presence of these rivers directly affects glacier movement, acting as a lubricating layer that allows ice to slide and shift in sudden bursts. Water at the ice base reduces friction between the glacier and bedrock, facilitating rapid surges that can temporarily increase flow rates by several meters per day. Observations indicate that subglacial water flow is linked with crevasse formation and changes in surface elevation, demonstrating that these rivers influence not only hidden processes, but also the behavior of the ice that can be measured from above. In this sense, the hidden water is not just passive, it is a controlling factor in ice dynamics. Certain channels carry water with surprising speed, linking subglacial lakes in connected networks that occasionally trigger sudden dramatic shifts in ice flow. When one lake drains, the downstream channels can suddenly swell, generating a pulse that ripples through the glacier and can even destabilize ice margins. These rapid flows resemble hydraulic surges in underground rivers on land, yet they occur beneath layers of ice that insulate and amplify their energy. The consequences of these surges are unpredictable, leaving researchers to wonder what pressures accumulate and what impact they may have on the ice sheet's overall stability. Even with sophisticated models and seasonal observations, predicting when and where these rivers will surge remains nearly impossible, as their paths are highly dynamic and sensitive to small changes. A minor increase in surface melting or a subtle shift in the glacier's slope can redirect entire flows, creating new channels or bypassing existing ones. Each summer brings a unique set of conditions, and no 2 years produce identical patterns of subglacial movement. The hidden rivers respond to forces invisible to observers, flowing according to rules that remain largely enigmatic. The hidden circulation beneath Greenland's ice has implications far beyond the glacier itself, influencing how rapidly ice may reach the ocean and contribute to global sea level rise. Faster flow facilitated by lubricating rivers can hasten ice discharge into fjords, potentially increasing calving events and oceanic contribution. Understanding these rivers is therefore critical not only for glaciologists, but also for climate scientists who model sea level change. Yet the more we learn about these hidden networks, the more questions arise about how vast and interconnected they truly are, and how they have evolved over millennia under conditions that humans have only begun to observe. Taken together, the subglacial rivers form a mysterious and largely unexplored system, a network of liquid currents quietly shaping the movement of an otherwise silent and frozen landscape. They defy easy measurement, their flows invisible yet powerful, affecting ice movement, subglacial pressures, and potentially even the stability of Greenland's vast ice sheet. Each new radar sweep or model output hints at more channels, more connections, and more unknowns, revealing an environment that is as dynamic and alive as any river network on the surface, but far more elusive and untouchable. Hidden deep within Greenland's ice, rivers of liquid water carve secret paths that shift the glacier above, leaving scientists to confront forces that remain entirely invisible and uncharted. The mysterious microbes living inside the ice. Deep within Greenland's ice, scientists have uncovered microscopic organisms that survive in conditions once thought completely uninhabitable, raising profound questions about the resilience of life. For decades, glaciers were viewed primarily as frozen archives of climate history, vast layers of compressed snowfall preserving traces of ancient atmospheres. Yet as researchers began examining ice cores more closely, they discovered something unexpected within these frozen layers. Living microbes quietly enduring in darkness and cold. Their presence suggests that Greenland's ice sheet is not merely a silent record of the past, but also a hidden habitat where life continues to persist against extraordinary odds. In a place defined by stillness and extreme cold, these tiny organisms represent a form of activity that scientists once believed impossible. The discovery relied on painstaking ice core analysis, where layers were carefully melted and filtered to reveal organisms invisible to the naked eye, demanding extraordinary precision to avoid contamination. Scientists must work in sterile laboratory environments, ensuring that modern microbes from the air or equipment do not compromise the samples. When the ice melts under controlled conditions, tiny cells sometimes emerge within the water, bacteria and other microorganisms that have been locked inside the ice for centuries or even longer. Each sample must be examined through microscopes and genetic sequencing, revealing traces of life that would otherwise remain completely undetectable. Even the smallest fragment of DNA can confirm that life once existed within a layer of ice that formed thousands of years ago. These microbes endure temperatures far below freezing, with minimal nutrients and oxygen, existing in a suspended state of near-complete dormancy that challenges conventional ideas of survival. In such conditions, biological processes slow dramatically, allowing cells to conserve energy and avoid damage. Some microbes appear capable of repairing their own DNA over extremely long periods, gradually maintaining their viability despite the harsh environment. This remarkable resilience forces scientists to reconsider the limits of life, suggesting that organisms can persist in places once assumed to be entirely lifeless. The deeper researchers look into frozen environments, the more they realize that life can adapt in ways that stretch the boundaries of biological expectation. Evidence suggests some of these life forms may have been trapped for tens of thousands of years, effectively preserved as a living record of ancient conditions long before modern humans walked the Earth. As snow accumulated and compressed into ice over millennia, microbes that once lived on the surface or in the atmosphere became sealed within the glacier. In this way, the ice sheet functions like a natural time capsule, storing biological material from distant periods of Earth's history. When researchers extract deep cores from Greenland's ice, they are not only retrieving frozen water, but also microscopic remnants of ecosystems that existed long ago. Some microbes may have entered the ice during ancient storms, carried by winds that swept across continents and oceans. To survive, the organisms employ unusual metabolisms, consuming trace gases or minerals, and sometimes producing antifreeze proteins that prevent ice crystals from destroying their delicate cells. These proteins allow microbes to maintain structural stability, even when surrounded by solid ice. Some bacteria can metabolize extremely small quantities of carbon or nitrogen compounds, sustaining themselves on chemical traces that would be insignificant to most other forms of life. These biochemical strategies reveal just how adaptable life can become when faced with relentless environmental pressure. Such adaptations demonstrate that even the most hostile environments can gradually shape organisms capable of enduring them. Rather than living in isolation, the microbes appear to form intricate hidden communities within tiny pockets of water or along mineral surfaces, creating ecosystems that operate entirely out of sight. Even in frozen environments, microscopic channels or thin films of liquid water can exist where pressure and chemical conditions permit. Within these minuscule habitats, microbes may interact with one another, exchanging nutrients or forming cooperative relationships that enhance survival. Though invisible to the naked eye, these communities represent a subtle web of life embedded deep within the ice. Their existence suggests that even the most isolated environments may contain complex biological interactions. These microscopic communities may even influence the ice itself, generating chemical byproducts or pigments that subtly affect melting patterns and the coloration of the surrounding ice. Certain microorganisms produce dark pigments that absorb sunlight more effectively than pure ice, potentially contributing to localized melting on glacier surfaces. Others release compounds that alter the chemistry of trapped water pockets, slowly changing the microenvironment around them. While these processes occur on an incredibly small scale, they remind scientists that even glaciers, often considered inert, can be shaped by biological activity. Over long periods, these subtle interactions could influence how parts of the ice respond to sunlight and environmental change. Studying them poses formidable challenges, as the organisms are fragile, sparse, and highly susceptible to contamination, meaning each sample provides only a tantalizing glimpse into an otherwise invisible world. Researchers must maintain sterile conditions at every stage of extraction and analysis. Even a single airborne bacterium could introduce misleading results. Because of these limitations, scientists often rely on genetic sequencing to identify microbial fragments rather than observing entire living colonies. Every confirmed discovery, therefore, represents careful work and cautious interpretation. In many cases, researchers must analyze multiple samples before they can confidently confirm that the microbes truly originated from the ice itself. Layers of ice harbour a record of Earth's climate and atmospheric composition, with microbial populations acting as microscopic archivists, silently preserving information about conditions spanning millennia. Different layers contain varying chemical signatures, and the microbes within them may reflect environmental changes that occurred when the snow first fell. By studying these biological traces, researchers can gain clues about past ecosystems, atmospheric conditions, and even ancient weather patterns. The ice sheet thus becomes both a geological and biological archive of Earth's evolving environment. Every new core extracted from the glacier offers another opportunity to uncover hidden details from the planet's distant past. The discovery of these organisms also expands the possibilities for life beyond Earth, suggesting that similar microbes could survive in the ice-covered oceans of moons such as Europa or Enceladus. These distant worlds possess environments where liquid water may exist beneath thick layers of ice, conditions that bear striking similarities to those found beneath Greenland's glaciers. If life can persist in Greenland's frozen darkness, it raises the possibility that microbial ecosystems might also exist in extraterrestrial icy habitats. For astrobiologists, the microbes hidden in Earth's glaciers offer a valuable model for understanding how life might endure elsewhere in the universe. The frozen environments of Earth, therefore, serve as natural laboratories for exploring the limits of biology. Despite advances in detection and analysis, the diversity, adaptability, and broader impact of Greenland's icebound microbes remain largely mysterious, hinting at processes occurring on a scale too small for human perception. Many microorganisms may still be undiscovered, concealed within layers of ice that have yet to be studied. Their metabolisms, interactions, and long-term survival strategies remain subjects of ongoing research. Each new sample deepens the intrigue, revealing a frozen environment that is far more biologically complex than once imagined. What scientists have uncovered so far may represent only a fraction of the life concealed within the vast ice sheet. Encased within Greenland's ancient ice, microscopic life persists in quiet isolation, hinting at hidden worlds of activity and resilience that may remain forever beyond our full understanding. The giant crater beneath Hiawatha Glacier. Aircraft radar scans over Hiawatha Glacier revealed an enormous circular depression in the bedrock, a discovery that immediately puzzled scientists studying Greenland's hidden geology. For decades, researchers had been mapping the ice sheet using airborne instruments designed to measure its thickness and the contours of the land below. Most of the radar images showed the expected irregular terrain: valleys, ridges, and ancient rock formations sculpted by glaciers long before modern ice covered the region. Yet within the data collected above this glacier in northwestern Greenland, something unusual began to appear: a nearly perfect circle carved into the underlying rock. At first glance, it seemed almost too symmetrical to be natural, prompting scientists to look more closely at the signals emerging from deep beneath the ice. During repeated flights over northwestern Greenland, airborne radar instruments began returning signals that gradually outlined an unusually symmetrical formation beneath the glacier. Ice-penetrating radar works by sending pulses of radio waves downward through the ice, where they reflect off the bedrock and return to the aircraft above. By measuring these reflections, researchers can construct detailed maps of landscapes that are otherwise impossible to see. As scientists processed the radar data from multiple flight paths, the circular structure became increasingly clear. The pattern appeared consistently in different surveys, eliminating the possibility that it was a simple error in the measurements. Spanning roughly 30 kilometers from edge to edge, this buried formation ranks among the largest impact structures ever identified on the planet. Its sheer size immediately suggested that an extraordinary force must have created it. On Earth, craters of this scale typically form when a large meteorite or asteroid collides with the planet at tremendous speed. Such impacts release energy equivalent to many nuclear explosions, excavating massive cavities in the crust and scattering debris over wide areas. Discovering a structure of this magnitude beneath Greenland's ice sheet raised an obvious question. Could this enormous depression be the scar of an ancient cosmic collision? Distinctive features visible in the radar imagery began to hint at a dramatic explanation for the structure's origin. The crater's edges appeared raised above the surrounding terrain, forming a ring that is characteristic of large impact sites. At the center of the structure, radar data suggested the presence of a slightly uplifted region, another feature often seen in large craters where rock rebounds after the initial impact. These patterns matched what geologists observe in well-known impact sites around the world. Although the crater remained buried under thick ice, its shape seemed to preserve the unmistakable signature of a violent event. Sediments carried away from the glacier have revealed unusual mineral grains that may trace back to a meteorite rich in iron. Researchers examining materials transported by meltwater streams near the glacier identified fragments containing elements commonly associated with iron meteorites. These fragments were discovered within sand and gravel deposited downstream from the glacier, suggesting they originated somewhere within the ice-covered region above. While the samples alone cannot confirm the crater's exact origin, they provide intriguing clues that something extraordinary once struck the ground beneath the glacier. Uncertainty surrounds the timing of the event, leaving researchers unsure whether the impact occurred before Greenland's modern ice sheet formed, or sometime after. Determining the age of a buried crater is extremely difficult when direct access to the bedrock is blocked by more than a kilometer of ice. Some scientists believe the impact could be relatively recent in geological terms, perhaps occurring during the last few million years. Others suggest it might be far older, formed long before ice sheets began covering this part of the Arctic. Without drilling directly through the glacier to reach the crater itself, the precise timing remains an open question. A collision powerful enough to excavate such a crater would have released enormous energy capable of melting vast quantities of ice and rock. When a large meteorite strikes the Earth, the force of the impact generates intense heat and pressure within seconds. Surrounding material can vaporize, melt, or fracture violently as the shockwave spreads through the crust. If such an impact occurred in Greenland while ice already covered the region, it might have produced dramatic floods of meltwater beneath the glacier. These possibilities remain speculative, but they illustrate how powerful the original event must have been. Over thousands of years, accumulating snowfall compressed into dense ice that gradually concealed the crater from direct observation. Greenland's ice sheet grows through the slow accumulation of snowfall that compacts into solid glacial ice over time, layer upon layer built up across the landscape, eventually burying the ancient crater completely. As the ice thickened, it preserved the structure below like a protective shield. Unlike craters exposed at the surface, which erode over time due to wind and weather, this one remained hidden and largely undisturbed. Reconstructing the crater's history remains difficult because the structure lies buried beneath more than a kilometer of glacial ice. Most of the information scientists have gathered so far comes from radar mapping and the analysis of sediments transported by meltwater. Drilling directly into the crater would provide much clearer evidence, but such an effort would be technically challenging in this remote Arctic environment. Until that happens, researchers must rely on indirect clues to piece together the crater's story. Radar maps now allow scientists to visualize a massive bowl-shaped depression surrounded by fractured rock and uplifted ridges. These images reveal a landscape that would look dramatically different if the ice was suddenly removed. Instead of a smooth glacier surface, the terrain below would display steep slopes descending toward the crater's center, with broken rocks scattered across its floor. The formation represents a moment when unimaginable energy reshaped the ground in an instant. Today, that violent history remains sealed beneath one of the largest ice sheets on Earth. Even with growing evidence, researchers are still piecing together what truly happened when the object struck this remote corner of Greenland. The crater's origin, its exact age, and its possible environmental consequences remain topics of ongoing investigation. Each new study adds another piece to the puzzle, yet many details remain uncertain. Greenland's ice sheet continues to conceal the full extent of what lies below, leaving scientists to interpret fragments of information gathered from far above the frozen surface. A vast circular scar rests beneath Hiawatha Glacier, suggesting that an immense collision once reshaped this remote corner of Greenland in ways scientists are only beginning to unravel. The unexplained signals detected beneath the ice sheet. Scientists monitoring Greenland's ice sheet have reported faint, unexplained tremors and pulses in their instruments, patterns that seem to originate from an unknown source below. For years, researchers had assumed that the ice moved in predictable ways, following patterns of seasonal melt, snowfall accumulation, and slow glacial flow. Yet every so often, signals appear that do not match these expected movements. Instruments pick up pulses with unusual timing, strength, or frequency, suggesting that something unseen is creating vibrations that propagate through kilometers of ice. These observations immediately caught the attention of glaciologists, geophysicists, and seismologists, all seeking to interpret what the data might reveal. The signals are faint but persistent, a quiet anomaly in a massive frozen environment. Some scientists have begun wondering if these disturbances might hint at processes so subtle and large-scale that they have never been fully theorized before, a reminder that Greenland's ice could conceal entirely new forms of dynamic behavior. Arrays of sensors, designed to measure vibrations and subtle shifts in the frozen environment, register fluctuations that can travel for miles through the ice. Seismic stations, sometimes placed in temporary camps or embedded into the ice, record even the smallest shocks that ripple across the sheet. Tilt meters, accelerometers, and specialized microphones pick up subtle changes that human senses cannot detect, translating them into data patterns for researchers to analyze. Over time, networks of these instruments have provided an unprecedented window into Greenland's interior, revealing that what appears static from above is actually alive with imperceptible motion. Yet within this wealth of data, certain anomalies stand out, demanding further scrutiny. The patterns sometimes suggest rhythms or sequences that almost feel intentional, as though the ice is subtly communicating its own hidden activity. Occasionally, these readings display rhythms that do not match typical glacial cracking, meltwater flow, or minor earthquakes, leaving researchers puzzled. Some signals are sharp and abrupt, resembling small seismic events, while others are continuous hums that last for hours. Their frequency and amplitude do not correlate with surface temperature, wind, or known ice movements, suggesting that they originate from processes that remain unobserved. Researchers cannot locate a single source for all these signals. Some seem to propagate along hidden channels, while others appear isolated, as though something under the ice is momentarily coming to life before fading away. There is a growing sense among some scientists that the signals may represent a combination of natural phenomena working together in ways that are still poorly understood. One hypothesis suggests that pressurized channels of water trapped under the ice might create transient pulses detectable far from their source. Subglacial lakes and rivers are known to exist beneath Greenland, carrying water that occasionally bursts through weak points in the ice. Sudden drainage events or shifting flows could generate vibrations strong enough for distant instruments to record. Yet the timing of the signals does not always coincide with expected meltwater behavior, and some occur in locations far from mapped subglacial water systems, leaving scientists uncertain whether water alone can explain the phenomenon. In some cases, bursts of activity appear to originate in areas previously thought to be dry and static. challenging long-held assumptions about the glacier's internal structure. Other possibilities point to the movements of massive ice sheets themselves, which under extreme stress can generate low-frequency vibrations that ripple across kilometers. As layers of ice slide past one another, immense pressure builds at points of friction, causing the ice to suddenly adjust. These adjustments can produce signals that resemble small tremors, but are difficult to predict. The complexity of the ice's internal structure, with its varying density, trapped air pockets, and hidden fractures, makes it difficult to fully model how these movements translate into detectable vibrations. Some of these pulses occur in seemingly random sequences, leaving scientists to question whether the ice contains a hidden network of shifting stress points that behave almost like a living system. Geological activity in Greenland's bedrock may also contribute, as slow tectonic shifts or rock fractures produce signals that occasionally intersect with those from the ice. Although Greenland is not a region known for major earthquakes, minor faults and slow-moving crustal processes can generate detectable energy. These tremors can propagate through both rock and ice, creating patterns that are challenging to distinguish from other sources. In some cases, signals appear simultaneously in multiple locations, hinting that they may originate from deep geological activity rather than surface or subglacial processes alone. Researchers remain careful not to overstate the case, but the combination of ice and rock vibrations produces a landscape of signals that is still largely unexplored. Some signals appear suddenly and then vanish, as if the ice is momentarily alive with sound, only to fall eerily silent moments later. Instruments have recorded pulses that last just a few seconds, leaving no trace behind, followed by long periods of inactivity. The fleeting nature of these signals frustrates efforts to triangulate their source or determine a clear cause. Scientists are left with fragments of data, puzzling over whether these ephemeral signals are the result of natural glacial dynamics, hidden water movement, subtle tectonic shifts, or something entirely unexpected. Some researchers even suggest that these fleeting signals could point to processes we have not yet imagined, phenomena that lie beyond conventional glaciology. Distinguishing meaningful patterns from background noise remains a challenge, as wind, temperature changes, and even equipment interference can obscure faint readings. Arctic weather conditions constantly produce minor vibrations and thermal expansion in the ice, all of which register on sensitive instruments. Researchers must sift through mountains of data to separate genuine anomalies from these predictable sources of interference. Statistical modelling, cross-referencing multiple sensor types, and repeated measurements are essential, yet even the most sophisticated analyses cannot fully explain some of the more unusual signals. In rare cases, the signals suggest a rhythm or occurrence that does not fit any known environmental factor, deepening the mystery. To improve clarity, researchers are installing additional instruments across more remote sections of the ice sheet, seeking continuous data to map these anomalies more precisely. Expanding coverage allows scientists to compare readings across long distances, helping to identify whether signals propagate in waves, originate from specific hotspots, or correlate with seasonal changes. Early results suggest that some signals are regional, affecting large portions of the ice, while others are highly localized, indicating that multiple processes may be responsible. Some pulses even exhibit subtle frequency shifts that hint at interactions between ice, water, and rock in ways still not fully understood. Every measurement reinforces the notion that Greenland's ice is far from inert, constantly producing subtle vibrations, shifting layers, and hidden movements that are only beginning to be detected. The ice sheet may appear motionless when viewed from the surface, yet instruments reveal a restless interior, alive with energy that escapes casual observation. These vibrations provide a window into processes that are both natural and enigmatic, illustrating the complexity of one of the largest ice masses on Earth. The signals continue to remind scientists that, even in regions thoroughly studied, the unknown remains vast and compelling. Even with expanding networks and ongoing analysis, certain signals resist explanation, hinting at processes that remain concealed from current scientific understanding. Researchers continue to debate potential sources, explore correlations, and test hypotheses, but some patterns persist without resolution. Each unexplained signal serves as a reminder that the ice sheet, despite decades of study, still holds secrets that have yet to be revealed. challenging assumptions about what lies beneath and inspiring further investigation. Unexpected bursts of activity pulse through the ice, hinting at forces and movements beneath Greenland's surface that science has yet to fully uncover. The strange meltwater tunnels that appear overnight. Researchers returning to familiar stretches of Greenland's ice sheet have sometimes discovered deep meltwater tunnels that were absent just a day before, as if the glacier itself had shifted overnight. These tunnels vary in size and complexity, from narrow channels barely wide enough to traverse to immense conduits that carve deep into the ice. Their sudden appearance has repeatedly surprised scientists, challenging assumptions about how quickly glacial ice can change. While surface melting is well documented, the speed at which these tunnels form hints at hidden forces within the ice, operating faster and more dynamically than conventional models predict. Each discovery prompts teams to reassess prior assumptions, questioning whether current knowledge of meltwater flow and subglacial hydraulics captures the full reality of Greenland's ice. Observing these formations in the field is often disorienting. Areas that seemed stable just hours earlier may now be dominated by entirely new channels. Instruments, satellite data, and aerial photography have collectively shown that this is not an isolated occurrence, but a widespread phenomenon across the ice sheet. Satellite images and aerial surveys have repeatedly captured these tunnels forming in plain sight, revealing patterns of ice carving that defy conventional expectations of slow, glacial change. Infrared and high-resolution imaging allow researchers to see subtle temperature and surface variations, which sometimes hint at where tunnels may soon emerge. These visual tools provide the first signs of motion within the glacier that might otherwise go unnoticed. Repeated imagery shows that even in areas previously mapped as featureless or solid, sudden depressions and channels appear, often overnight. Each new satellite pass seems to reveal a different puzzle, with some tunnels connecting to existing crevasses while others defy apparent logic, snaking in unexpected directions. The ability to observe these transformations from above has expanded scientific awareness, yet it also deepens the mystery. The ice is capable of rapid, unseen restructuring that is both mesmerizing and unsettling. While some tunnels align with known crevasses or meltwater channels, many emerge in locations where no prior mapping suggested water flow, leaving scientists puzzled by their distribution. In some cases, tunnels appear in the middle of vast ice plains, far from slopes or known meltwater sources. This randomness challenges assumptions about gravitational drainage and established glacial dynamics. Researchers have noted clusters of tunnels in certain regions, but even within those clusters, the formation seems unpredictable, with new paths appearing without precedent. Mapping efforts reveal that no single environmental factor, surface slope, temperature, or precipitation, consistently predicts the tunnel's locations. The irregularity of these formations suggests an underlying process operating beneath the surface, hidden from observation, and possibly connected to complex interactions between ice, subglacial water, and the bedrock below. Several theories attempt to explain the sudden formation, including pressure-driven subglacial drainage, rapid ice melting from surface meltwater percolation, or abrupt structural collapses within the glacier, yet none fully accounts for the speed or scale. Laboratory experiments and computer modelling replicate some aspects of tunnel formation, but fail to capture the overnight emergence observed in the field. Some scientists hypothesize that pockets of pressurized meltwater, trapped under ice layers, may suddenly breach weak points, releasing energy that carves channels rapidly. Others point to internal ice fractures that propagate unpredictably, allowing water to exploit unseen weaknesses. Despite these possibilities, no single model explains why some tunnels form without detectable precursors, suggesting that Greenland's ice still harbours processes beyond current scientific comprehension. Some tunnels stretch for hundreds of meters, their walls smooth and uniform, while others twist and branch unpredictably, suggesting forces at work that are still poorly understood. In certain locations, the tunnels intersect, creating networks of hidden waterways beneath the surface. Observations indicate that water pressure alone cannot account for the tunnel's shapes. The ice itself appears to shift or collapse in coordination with the flow, as if responding to internal cues beyond simple hydraulics. The variety of tunnel forms, straight, curved, branching, or sinuous, implies a combination of forces at work including melting, pressure redistribution, and subtle movement of ice layers. Field measurements reveal tunnels that widen or narrow dramatically, indicating fluctuating pressures and unstable internal structures. Such variability complicates efforts to predict where new channels will appear, leaving researchers to rely on continuous observation. Even tunnels of similar size and length exhibit different internal textures, suggesting that multiple factors, thermal, mechanical, and hydrological, interact to shape each formation. The sudden emergence of these tunnels can temporarily alter local ice stability, redirecting water flow, relieving pressure in some areas, and intensifying strain in others, hinting at dynamic processes operating beneath the surface. In some cases, a tunnel may relieve pressure in a section of the ice, preventing surface cracking, while nearby regions experience increased tension. These transient effects are not only fascinating but may influence larger-scale ice sheet behaviour over time. Researchers suspect that repeated tunnel formation in certain zones could gradually weaken structural integrity, potentially contributing to ice collapse or accelerated glacial movement. Each new formation acts as a brief, unpredictable event that reshapes local drainage patterns, sometimes connecting to subglacial lakes or disappearing without a trace. Close examination of some tunnels reveals unusual features: sharply curving paths, abrupt expansions in width, or openings connecting to unknown subglacial reservoirs, emphasizing the enigmatic nature of their formation. In rare instances, tunnels contain small frozen pockets or sediment deposits that hint at interaction with underlying bedrock or ancient glacial debris. These details suggest that the tunnels are more than superficial drainage channels. They may serve as transient conduits for energy and water beneath the ice. The internal composition of walls, from crystalline ice to compacted snow layers, varies along the tunnel's paths, adding complexity to any explanation. Collectively, these features hint at hidden processes that may link surface melting, subsurface water, and internal ice dynamics in ways still not fully understood. Although many tunnels coincide with seasonal melt or warmer temperatures, some appear during unexpectedly cold periods, suggesting that formation triggers may involve hidden interactions between ice, water, and geological features. Data indicate that not all tunnel formation is temperature dependent. Some occur in regions of thick ice where surface melt is minimal. Researchers are left to consider the possibility of stress-driven cracking or subglacial hydraulic surges that operate independently of direct melting. The lack of predictable environmental triggers challenges traditional assumptions about glacial dynamics and forces scientists to reconsider how quickly ice sheets can respond to subtle internal changes. Studying these ephemeral structures is notoriously difficult. By the time a research team reaches the site, the tunnel may have partially collapsed or completely disappeared, leaving only subtle depressions or meltwater traces. Even with drones, satellite imagery, and field sensors, the fleeting nature of these formations makes capturing them in real time nearly impossible. This rapid evolution adds a layer of intrigue, as scientists can observe the aftermath but rarely witness the moment of creation. The impermanence of tunnels forces researchers to rely on indirect data, making inferences from water flow, ice movement, and remote sensing patterns. The phenomenon has increasingly drawn scientific attention, prompting glaciologists to deploy denser observation networks, test novel imaging techniques, and develop models that attempt to capture the rapid, unpredictable behavior of the ice. International teams now collaborate to track tunnel emergence, seeking correlations with seasonal cycles, subglacial lakes, or structural ice weaknesses. Early modelling efforts show potential explanations but consistently fall short of capturing the full speed and variety of observed events. Researchers remain motivated by the knowledge that these tunnels represent a facet of Greenland's ice that is still largely invisible, offering a glimpse into forces operating on both human and geological timescales. Even after years of monitoring and advanced modelling, some meltwater tunnels continue to appear overnight without explanation, defying attempts to predict their timing, path, or scale. Each new tunnel reminds scientists that Greenland's ice is not a static, unchanging mass, but a living system capable of reshaping itself in ways that challenge understanding. These formations, though transient, leave lasting questions about how water, ice, and pressure interact beneath the surface, and what unseen processes remain concealed within the sheet. By dawn, the ice may conceal new passages carved in secret, leaving researchers to trace patterns that vanish almost as soon as they are discovered. The ancient forest buried beneath the ice. Fragments of wood and pollen discovered deep within ice cores revealed a forest that had once thrived in Greenland, frozen yet preserved for millennia. Scientists were stunned by the survival of these remnants, which suggested a thriving ecosystem existed in a region now dominated by ice. Each core sample offered clues about climate, vegetation, and the slow encroachment of glaciers that ultimately buried the forest. Laboratory analysis began to uncover its composition, raising questions about how such life could exist in what is today an extreme polar environment. Even small amounts of pollen offered insight into the diversity of plant life and seasonal growth cycles. Over time, patterns emerged, revealing a forest with multiple species and layered vegetation. Every discovery deepened the mystery. How did this ecosystem thrive, and what could its survival tell us about Greenland's ancient past? Researchers first noticed anomalies in sediment layers, unusual organic traces that hinted at life existing in a climate radically different from today's frozen expanse. Tiny inclusions of moss and plant matter suggested parts of the landscape had been vegetated long before glacial expansion. Sediment cores revealed alternating layers of organic material and mineral deposits, implying environmental changes that allowed tree growth. By analysing the microscopic composition of each layer, scientists began reconstructing the forest's ecological history, showing pockets of dense woodland and open clearings. Observations suggested that the forest was resilient, capable of surviving variable conditions for extended periods. The sediment layers became a map of forgotten landscapes, whispering secrets of a Greenland that once teemed with life. Radiocarbon analysis confirmed the plant material originated from a period when temperatures allowed tree growth, suggesting the island once hosted dense woodland. Dating revealed some fragments were tens of thousands of years old, preserved through successive glacial advances. This timing coincided with known warm periods in Earth's history, yet the scale of vegetation implied local conditions were far more favourable than previously assumed. Pollen grains extracted from the ice cores indicated the prevalence of both deciduous and coniferous species, revealing a forest capable of supporting diverse life forms. Radiocarbon results also hinted at periods of abrupt environmental change, when ice may have advanced rapidly, encasing the forest. Botanical studies indicate birch, alder, and mosses formed a complex ecosystem, with intertwined roots and layered vegetation that hint at a surprisingly rich prehistoric habitat. The arrangement of these species suggests seasonal cycles with periods of rapid growth and dormancy. Moss coverage indicates microhabitats supporting moisture retention and nutrient cycling. Pollen analysis shows evidence of flowering plants, offering clues about pollination and seasonal patterns. Fossilized remnants suggest the forest existed in groves rather than a continuous canopy, hinting at localized ecological diversity. Understanding the forest's makeup allows scientists to reconstruct the climate and environmental pressures of its era. The forest preservation is owed to rapid burial, low temperatures, and protective sediment layers that prevented decay for thousands of years. Compression from advancing ice sheets likely prevented oxygen from reaching delicate tissues, halting decomposition. Fine silt and mineral layers acted as shields, protecting wood, roots, and moss from microbial attack. Even small depressions in the bedrock may have helped funnel ice and sediment over the forest. The conditions preserved tree rings and cellular structures, offering a rare glimpse into the life history of these long-extinct trees. Climate reconstructions show this vegetation existed during warmer intervals, challenging previous assumptions about Greenland's ancient environmental history. These periods provided enough time for forests to grow and mature. Isotopes in plant tissue indicate higher average temperatures than today, with precipitation patterns supporting consistent hydration. The existence of forests implies Greenland's ice sheet was not as extensive or permanent during these periods. Paleoecological data point to cycles of growth and glacial encroachment, creating a patchwork of forested and ice-covered zones. Evidence suggests glaciers and sediment gradually advanced over the forest, encapsulating its remains in a way that preserved both structure and composition. Ice sheets may have slowly flowed over valleys, pressing soil and organic matter into compact layers. Meltwater percolating through sediment could have softened the ground, allowing some trees to topple yet remain intact. Geological surveys indicate these processes occurred unevenly, resulting in pockets where trees survived with minimal disturbance. The glacier acted both as a destructive and preservative force, simultaneously burying and safeguarding the forest for millennia. Ice melt and surface exposure in modern times have revealed stumps, fragmented logs, and patches of moss, offering researchers fleeting glimpses into this long-hidden ecosystem. Field teams documenting exposed sections find tree trunks partially embedded in ice, with bark and fine root networks still identifiable. Small patches of moss clinging to wood provide rare evidence of biological survival beneath cold conditions. Each new exposure generates excitement and urgency, as thawed sections may quickly erode or collapse. Drones and satellite imaging assist in locating newly revealed sites, enabling rapid study. Every glimpse contributes pieces to a larger puzzle, slowly revealing Greenland's lost forests. Some discoveries defy explanation. Perfectly preserved tree rings, upright root systems, and unexpected plant combinations suggest ecological conditions that remain mysterious. Rings reveal growth rates inconsistent with known climate patterns, hinting at microclimates or unique seasonal cycles. Root structures indicate trees adapted to variable soil depths and shifting sediment layers. These anomalies suggest environmental pressures were both harsh and highly selective, yet allowed pockets of biodiversity to endure. Each unusual feature reinforces the sense that Greenland's ice conceals secrets, not only of survival, but of ecological adaptation beyond current knowledge. The buried forest offers insights far beyond Greenland, informing global studies of paleoclimate, species migration, and ice sheet evolution. Similar buried ecosystems exist in other Arctic regions, but Greenland's forest is unusually extensive and well preserved. Comparing its remnants with other sites allows scientists to reconstruct climate patterns, track shifts in vegetation zones, and better understand glacial cycles. The findings contribute to debates on how ecosystems respond to rapid environmental change. Each sample informs models predicting how current glaciers may respond to climate warming, offering a rare window into resilience and adaptation over millennia. The forest continues to baffle scientists, leaving unanswered questions about how it survived, what caused its burial, and what hidden remnants might still linger beneath the ice. Even with careful excavation and analysis, much of the forest's history remains obscured, and each discovery raises new questions about Greenland's prehistoric landscape. As the ice gradually retreats, fragments of this ancient woodland emerge, hinting at a Greenland that existed long before human eyes ever charted its frozen reaches. The mysterious rumbling from Jakobshavn Glacier. A deep, resonant vibration occasionally shakes the air near Jakobshavn Glacier, reverberating across the ice in ways that defy conventional measurement. Researchers report that the sound is not a sudden crack or collapse, but a sustained low-frequency hum that seems to originate from deep within the glacier itself. Instruments placed on the surface often detect subtle ground motions that coincide with the audible rumble, though the magnitude varies dramatically and unpredictably. The phenomenon has puzzled glaciologists for years, prompting investigations into every possible explanation from ice fractures to subglacial water movement. Field scientists describe the sensation as both eerie and disorienting, a tangible reminder that the glacier is not a static mass, but a dynamic, living structure. Even when temperatures stabilize and surface melting slows, the hum can return without warning, indicating forces beyond simple seasonal cycles. Its irregularity challenges current models of glacier physics, revealing unknown aspects of ice sheet behavior. The sound can travel for miles, echoing across fjords and valleys, leaving observers with the sense that the ice itself is communicating in a language yet to be deciphered. Each new observation only deepens the mystery, emphasizing the unpredictable nature of one of Greenland's most famous glaciers. Historical accounts from early explorers and Inuit communities mention sounds like distant thunder, often coinciding with sudden tremors that left little trace on the ice itself. Old travel diaries and oral histories describe rolling rumbles felt during calm days when no visible carving occurred, hinting that this is not solely a modern phenomenon. These reports suggest the glacier's subtle movements were noticed long before the advent of scientific instruments capable of quantifying vibrations. In some cases, Local communities interpreted the sounds as warnings or omens, a reflection of their intimate understanding of the environment. Early 20th century surveys documented minor icequakes, though the full significance of these recordings was not understood until decades later. Even with limited data, patterns began to emerge. The rumbling was irregular, sometimes spaced days apart, other times clustered over weeks. Such variability reinforced the idea that Jakobshavn Glacier operates according to forces that remain largely hidden. The historical record thus adds a layer of temporal depth to the mystery, connecting contemporary observations with centuries of unexplained phenomena. Modern monitoring stations capture subtle pulses that do not align with expected ice movement, revealing irregular patterns in frequency and intensity that baffle glaciologists. Arrays of seismographs, GPS units, and acoustic sensors track both the glacier's surface and the underlying bedrock, yet they fail to produce consistent explanations. Data occasionally shows vibrations with amplitudes comparable to minor earthquakes, but without corresponding shifts in ice flow or calving events. Researchers have compared these signals to recordings from other glaciers worldwide, only to find that Jakobshavn's rumbling is unusually persistent and variable. Its low-frequency characteristics suggest an origin deep within the ice or bedrock, beyond the reach of surface-level observation. These readings challenge standard models of glacial dynamics, forcing scientists to consider interactions between ice, water, and the underlying geology in novel ways. Each new dataset raises more questions than answers, emphasizing the complexity of forces acting within Greenland's ice sheet. Standard glacier dynamics, crevasse formation, calving events, and basal slip account for some rumbles, yet they fail to explain the most isolated and prolonged vibrations. Ice cracking produces sudden, sharp sounds, while calving results in booming crashes. The continuous hum of Jakobshavn Glacier does not match either pattern. Basal slip, where the glacier slides over its bed, contributes some low-frequency movement, but the signals often persist even when surface flow slows. This discrepancy has led scientists to propose that additional unknown factors are at play, perhaps originating from deep within the ice or bedrock. The glacier's internal structure, with its network of crevices, channels, and pressure zones, may generate vibrations that propagate unpredictably. Observers in the field report that the rumble sometimes precedes visible ice movement, implying that the glacier is active below the threshold of human detection. Understanding these subtle dynamics is essential for predicting future calving and the behavior of the ice sheet. Seasonal shifts bring fluctuations in ice speed and meltwater flow, occasionally intensifying the low, rolling hum in ways that resist clear correlation with temperature or precipitation. During summer months, surface meltwater can penetrate cracks and reach the glacier base, potentially lubricating the ice and amplifying vibrations. Yet scientists note that similar rumbles occur in the winter, when meltwater is minimal and the surface is largely frozen. This seasonal inconsistency complicates the search for a definitive cause. Periods of accelerated ice movement, sometimes linked to rapid calving events, coincide with louder and more frequent hums, but not consistently enough to establish causation. The interplay between environmental conditions, ice mechanics, and subglacial processes appears far more intricate than initially anticipated. As researchers analyze long-term datasets, patterns emerge sporadically, emphasizing the glacier's enigmatic and unpredictable nature. Hidden channels of subglacial water may act as amplifiers, sending pressure waves across kilometers of ice, yet the exact mechanisms remain elusive and unpredictable. Mapping these conduits is challenging, as radar and sonar surveys must penetrate thick ice, while distinguishing between water, sediment, and bedrock. Water can increase basal pressure, creating vibrations that resonate through the glacier like an underground orchestra. Yet simulations and field measurements show that not all rumbling can be explained by water flow, suggesting additional forces at work. Scientists hypothesize that the geometry of subglacial channels, combined with ice density variations, may produce unique acoustic effects. These hidden pathways may also shift over time, altering how vibrations propagate. The result is a rumble that defies replication, leaving even the most advanced instruments struggling to capture its full scope. Scientists and field researchers recount moments when the ground trembles or the air vibrates without any visible ice movement, reinforcing the sense that the glacier holds unknown forces. Teams working near calving fronts or along fjord edges often feel subtle shakes, sometimes accompanied by the distant hum. Equipment may detect small tremors that correlate with the vibrations, but the ice shows no corresponding displacement. Such experiences challenge assumptions about glacial stability, highlighting the difference between what is seen and what is sensed. These anomalies underscore the glacier's ability to generate activity beyond immediate observation, reminding researchers that ice is both massive and elusive. Acoustic analysis reveals anomalous signatures, with frequencies and amplitudes unlike those of ordinary icequakes, hinting at processes that conventional theory cannot fully describe. Specialized sensors measure tones below the range of human hearing, capturing signals that spread slowly across the glacier. Some frequencies appear to reverberate through the ice in patterns resembling resonance, but no consistent source has been located. Researchers compare these signals with known seismic and glacial data, yet a portion remains unexplained. The presence of these mysterious acoustic phenomena suggests that Jakobshavn Glacier has dynamic processes hidden beneath its surface that are not yet understood. Below the ice, bedrock fractures or geothermal activity may contribute to the phenomenon, but mapping and measurements have yet to pinpoint a definitive source. Tectonic features beneath Greenland are poorly documented in some regions, leaving open the possibility that small faults or fractures generate subtle tremors. Heat flow anomalies could also produce pressure changes within the ice, though direct evidence remains scarce. The combination of geological and glacial interactions creates a complex system where multiple forces converge, producing vibrations that appear independent of visible ice motion. Investigating these factors is crucial for understanding the glacier's behavior and potential impacts on surrounding fjords. Understanding these rumblings carries profound implications for glacial stability and sea level projections, as unpredictable vibrations may signal hidden weaknesses within the ice sheet. If these subtle tremors indicate fractures or destabilization zones, large-scale calving events could occur with minimal warning. Ice sheet models must account for these anomalies to more accurately predict the response of Greenland's glaciers to warming temperatures. The rumbles may also inform understanding of subglacial hydrology and bedrock interactions, revealing forces previously overlooked in climate and geological studies. As the glacier moves, it continuously challenges assumptions about what ice can do beneath the surface. Despite continuous observation and advanced instrumentation, the glacier continues to generate pulses that resist explanation, leaving researchers in a state of quiet vigilance. Even with real-time data and historical records, no single factor accounts for the full scope of the rumbling. Each new observation highlights the glacier's complexity and its capacity to surprise those who study it. Scientists remain attentive, aware that the glacier's subtle movements may hold clues to processes that are as important as they are mysterious. Scientists strain to interpret the sounds, yet the glacier's subtle tremors seem determined to guard their secrets in silence. The strange blue lakes that suddenly appear on the ice. An impossible hue suddenly appears atop the ice, vivid and almost surreal, catching the eye with a brilliance that contrasts sharply with the surrounding white expanse. These sudden blue lakes are not illusions, yet their formation often defies conventional explanations. Some emerge as perfectly circular mirrors, others as jagged depressions filled with electric azure water, shimmering under the low Arctic sun. Even satellite imagery can struggle to capture their fleeting presence, as many appear and vanish within days. The pool's vibrant colour stems from a combination of ice density, light absorption, and water clarity, creating an intensity that immediately draws attention. Field teams navigating the glaciers often arrive to find these pools already present, their boundaries sharp and depths uncertain. Rapidly forming, they can reach volumes rivaling small ponds, yet vanish almost as quickly. Instruments measure temperature, depth, and volume, but patterns remain inconsistent, challenging established hydrological models. Some lakes form near visible crevasses, while others appear atop seemingly solid ice, leaving no surface evidence of water movement beneath. Drone footage reveals sudden changes in surface reflectivity, but cannot explain the source. The speed and unpredictability of these formations suggest hidden processes, possibly linked to subglacial water channels or transient melt events that have yet to be fully documented. Satellite observations occasionally capture clusters of these lakes, revealing appearances across vast stretches of the ice sheet. Some form in isolated pockets, while others appear in networks suggestive of underlying conduits. The lake's fleeting nature complicates study. By the time high-resolution images are analysed, many pools have drained or refrozen. Thermal imagery shows slight heat anomalies, hinting at subsurface water or ice deformation, yet it does not consistently predict lake formation. Seasonal patterns help explain some appearances, but the timing of certain pools defies expectations, emerging outside predicted melting windows. These ephemeral formations highlight that Greenland's surface and subsurface hydrology are far more dynamic than previously understood. Seasonal sunlight and melt influence the creation of many blue lakes, yet numerous instances occur under conditions where sunlight alone cannot account for the water accumulation. Low temperatures and sparse surface melt suggest water may be rising from below or pooling in concealed depressions. Some lakes form where snow cover is continuous, indicating that liquid water navigates unseen channels before breaching the surface. Other occurrences appear shortly after minor ice fractures or crevasse activity, hinting that structural shifts might trigger sudden ponding. Observed timing sometimes conflicts with predictive hydrological models, emphasizing the complexity of ice-water interactions. These contradictions have led scientists to reconsider assumptions about ice sheet behavior and meltwater transport. The lake's electric blue color fascinates observers, resulting from the absorption of red light and scattering of shorter wavelengths by dense, clear water. Deeper pools appear darker, while shallow depressions glow turquoise. Some exhibit subtle iridescence caused by suspended microbubbles or thin ice layers on the surface. Chemical analyses reveal only minor variations in water composition, suggesting that color differences largely stem from optical factors rather than contaminants. The contrast between vivid water and stark ice creates a visual effect that is at once beautiful and unnerving. Each lake becomes a fleeting spectacle, an enigmatic feature that demands both observation and caution. Hidden subglacial channels likely direct water into basins, shaping these transient lakes. Ground-penetrating radar has revealed networks of cavities and conduits beneath the ice that might store and release water suddenly. These channels could explain the rapid formation of some pools, although they cannot account for all occurrences. In areas without mapped conduits, lakes emerge unpredictably, raising questions about undiscovered subsurface pathways or pressurized reservoirs. Ice deformation may temporarily trap water until pressure or minor fractures release it, forming visible lakes. The interactions of hidden channels, ice structure, and meltwater demonstrate a complexity that is only partially captured by current observational methods. Time-lapse studies document lakes appearing within hours or overnight, some merging into larger bodies, others remaining isolated. Rapid formation defies conventional melt rate calculations, suggesting that subsurface dynamics or stored meltwater play a role. Water movement can occur silently, producing minimal surface disruption, yet small shifts in surrounding ice are occasionally observed. The lake's sudden appearance provides unique opportunities to monitor ice-water interactions in real time. Repeated formations in similar locations indicate certain areas may be predisposed to pooling, though precise triggers remain uncertain. These observations highlight how much remains hidden beneath the glacier's surface, unseen until water emerges. Many lakes vanish as abruptly as they form, draining through cracks, flowing into hidden channels, or refreezing entirely. Draining often leaves the ice deceptively smooth, erasing visible signs of water movement. Refreezing can isolate water under thin ice, creating hidden hazards. Some lakes disappear without audible cracking, while others produce subtle sounds, reflecting minor stress adjustments in surrounding ice. This unpredictability hinders long-term mapping and complicates efforts to understand water flow beneath the glacier. Each disappearance underscores the transient and enigmatic nature of these blue pools, reminding researchers that Greenland's ice can rearrange itself in ways that are almost impossible to predict. Unexpectedly, some lakes appear in regions without clear surface melting, defying simple explanations. Microclimatic effects, ice density variations, or pressurized subglacial water may contribute. Occasionally, lakes form at high elevations or on slopes shielded from direct sunlight, challenging assumptions about meltwater sources. These occurrences suggest hidden energy, water storage, or movement mechanisms within the ice. Patterns may repeat annually, but with inconsistent timing, adding to the mystery. Even with comprehensive monitoring, some lakes emerge without apparent precursors, emphasizing the glacier's ability to surprise and revealing that much remains unknown about ice sheet hydrology. Each new blue lake demonstrates that Greenland's ice sheet is far from static. Minor variations in ice structure, hidden crevasses and pressure fluctuations may collectively trigger surface pooling. Some lakes appear randomly, while others cluster in apparent alignment with subsurface channels. These transient features serve as natural experiments, exposing the glacier's responsiveness to both internal and external forces. Each formation offers insight into complex ice dynamics, yet also reminds observers of the limits of current knowledge. The ephemeral nature ensures that every lake is unique, unrepeatable, and shrouded in mystery. Continuous observation and modelling have yet to predict the lake's timing or location with accuracy. Even with improved sensors and satellite imaging, pools continue to emerge unpredictably. Some patterns are discernible on broader scales, yet individual lake formation defies precise forecast. Subtle ice properties, internal water flow, and environmental variability all contribute, creating a tableau that is both scientifically intriguing and visually striking. The transient brilliance of these lakes highlights the glacier's hidden activity and reinforces that every discovery is only a partial glimpse into Greenland's complex ice systems. Interactions between surface melting, subsurface water, and ice structure create conditions that remain largely unexplained. Each new pool challenges existing hydrological models, revealing processes that operate faster and more unpredictably than anticipated. Even extensive measurement and monitoring capture only a portion of the activity, leaving questions about source, timing, and disappearance. Every observation underscores the need for continued study, but also the limits of current scientific tools in capturing a system in constant motion. Greenland's ice continues to reveal its hidden complexity, offering fleeting glimpses of processes that remain beyond full comprehension. Each blue pool vanishes as if conjured, leaving the frozen expanse to conceal its fleeting brilliance in silence. The ice that moves faster than predicted. Remote monitoring has revealed a startling phenomenon. Glaciers in certain regions of Greenland are advancing at speeds far beyond what established models anticipated. Satellite imagery and field measurements show ice shifting in unexpected ways, often accelerating without apparent cause. Researchers tracking these movements have noted that even minor variations in surface temperature or meltwater presence can provoke sudden speed changes, though the exact mechanisms remain elusive. The ice sheet, long considered a relatively stable environment, now presents a dynamic and mysterious force, challenging decades of predictions about its flow and stability. These anomalies are not isolated. Multiple regions display similar patterns, hinting at underlying processes yet to be fully understood. Data collected through GPS sensors and satellite interferometry show bursts of motion that defy expectations, sometimes doubling predicted ice flow in mere days. Stations embedded in the ice provide real-time tracking, revealing pulses of movement that arrive and vanish without warning. Glaciologists have documented intervals of calm interrupted by rapid surges, suggesting that the ice behaves less like a slow-moving mass and more like a living system with hidden triggers. These bursts, while measurable, resist simple categorization, and the velocity fluctuations challenge standard models of ice dynamics. Each dataset raises further questions about how energy is transferred through the ice and what unseen forces might be accelerating its motion. Historical records of ice movement suggested steady, gradual progression, yet current measurements reveal irregular surges that challenge decades of assumptions. Observers once relied on long-term surveys and seasonal observations to estimate glacier behavior, assuming a slow and predictable pace. Comparing those older estimates to today's satellite data highlights stark discrepancies, with some glaciers advancing at nearly double the expected rate. These unexpected accelerations suggest that previously unconsidered factors, such as basal lubrication or internal ice fracturing, may play a far more significant role than anticipated. Such contrasts between past and present behaviour deepen the sense of mystery surrounding Greenland's ice sheet. Beneath the frozen surface, basal layers of ice and water interact in ways that remain only partially understood, influencing the glacier's velocity unpredictably. Meltwater can seep through cracks, forming thin films that reduce friction, while pressure variations may force the ice to deform internally. Researchers have observed that these basal processes do not act uniformly. Localized areas experience more rapid sliding, contributing to irregular flow patterns. This subsurface activity is difficult to monitor directly, relying on indirect measurements such as seismic tremors or radar echoes. The ice's hidden layers behave like a complex network of conduits and cavities, where small changes can provoke sudden dramatic shifts in movement. Subsurface cavities and hidden meltwater channels appear to act as unseen highways, enabling portions of the ice sheet to glide with sudden intensity. These networks, often invisible from the surface, can transport water over long distances, lubricating basal interfaces and triggering acceleration events. Researchers using ice-penetrating radar have mapped portions of these channels, revealing intricate labyrinths that defy simple interpretation. The complexity of these networks suggests that Greenland's ice is not a uniform sheet but a patchwork of interdependent systems, each contributing to unpredictable flow patterns. The discovery of these hidden conduits has opened new avenues for study while amplifying the sense of uncertainty surrounding ice dynamics. Certain glaciers exhibit episodic accelerations, often linked to seasonal melt or snowfall, though the timing and magnitude often confound even the most precise models. In spring and summer, surface meltwater infiltrates the ice sheet, sometimes triggering sudden pulses of motion that persist for days or weeks. Scientists have noted that these events do not always align neatly with temperature or precipitation patterns, implying additional hidden mechanisms at work. The unpredictability of these accelerations complicates forecasting, particularly when attempting to anticipate potential impacts on calving fronts or sea level rise. Each observed surge reminds researchers that even well-studied glaciers can behave in astonishingly complex and unexpected ways. The consequences of these rapid flows ripple outward. Calving rates increase, ice sheet stability fluctuates, and local topography shifts in subtle, sometimes invisible ways. Accelerated ice movement can strain glacier termini, causing chunks to break away more frequently and altering fjord dynamics. The effects extend to surrounding ecosystems, as sediment and meltwater discharge reshape coastal environments. Even minor fluctuations in velocity can have cascading impacts, revealing the interconnectedness of ice, water, and land. These changes occur quietly beneath the surface, and can only be fully appreciated through detailed long-term monitoring and careful analysis, emphasizing the fragile balance of Greenland's frozen landscape. Harsh conditions and the sheer scale of Greenland's ice sheet make accurate, continuous measurement difficult, leaving large gaps in the understanding of these accelerated movements. Instruments can fail under extreme cold, and satellite passes are limited by orbit schedules and cloud cover. Field teams face logistical constraints, travelling across crevassed terrain and unpredictable weather, all while attempting to gather reliable data. Despite technological advancements, the ice sheet retains vast regions that remain effectively unobserved, meaning that rapid accelerations could occur in areas entirely unknown to science. This inaccessibility amplifies the sense of mystery, as researchers can only speculate about the forces driving movement in unseen portions of the glacier. Researchers debate competing explanations, from basal lubrication by meltwater to internal stress redistributions, yet no single theory fully accounts for the observed speed. Some argue that transient hydrological networks beneath the ice create pulses of motion, while others suggest that internal ice crystal deformation plays a critical role. Still, none of these hypotheses alone can explain the magnitude or irregularity of the accelerations observed. The scientific dialogue remains open, with each new observation prompting re-evaluation and sometimes entirely new models of glacier dynamics. The debate itself underscores how little is truly known about the forces shaping Greenland's fastest-moving ice. Patterns emerge sporadically, with some glaciers exhibiting bursts while neighbouring ice remains largely stagnant, hinting at complex forces hidden within the ice. Researchers have noted that even glaciers separated by only a few kilometres can behave entirely differently, responding uniquely to local topography, meltwater input, and internal stress. These inconsistencies defy simple correlation with climate variables, suggesting that internal ice dynamics exert a dominant though largely unobserved influence. The irregularity of these patterns creates a persistent puzzle. How can such vast sheets of ice move in radically different ways, despite being subject to the same overarching conditions? Each anomaly adds to the sense of awe and uncertainty. Each observation reinforces the idea that the ice sheet is a dynamic entity, capable of movements that defy both expectation and prediction. No longer can Greenland's glaciers be viewed as static or slowly evolving. They're active participants in an environment governed by both visible and hidden forces. As scientists refine measurements and develop more sophisticated models, the ice continues to surprise, accelerate, and defy expectations. The combination of unpredictability, hidden mechanics, and environmental influence creates a landscape that is simultaneously measurable and unknowable, a frozen world that retains its secrets despite decades of investigation. The ice's sudden, silent rush continues to rewrite the rules of a frozen world, revealing forces that elude even the most careful observation. The unusual methane trapped beneath the ice. Methane has been accumulating in unexpected pockets within Greenland's ice, presenting scientists with concentrations that defy conventional models. Field teams examining ice cores and subglacial sediments have discovered readings far higher than anyone anticipated, prompting questions about what forces have preserved these gases for centuries. The frozen layers, once considered largely inert, now appear to conceal dynamic chemical processes and pockets of energy whose behaviour remains largely mysterious. Each measurement amplifies the sense that the ice sheet is more than a static landscape. It is a vault of hidden processes, quietly shaping the environment in ways scientists have only begun to understand. Ice core records hinted at trace gases over the decades, but recent measurements show volumes far exceeding any previously recorded levels. These cores, drilled thousands of meters into the ice, contain evidence of methane concentrations that would have been impossible to detect with earlier techniques. Layer upon layer tells a story of gases trapped and preserved, occasionally punctuated by microbubbles that provide snapshots of ancient atmospheres. The accumulation suggests that Greenland's ice is not simply a passive repository, but a complex system interacting with subglacial sediments and the surrounding environment, holding energy that may be released under unknown conditions. Subglacial sediments compacted over millennia seem to act simultaneously as reservoirs and seals, containing gas that could otherwise escape into the atmosphere. Organic matter trapped beneath the ice decays slowly, producing methane that becomes encased within sediment pockets or small water-filled cavities. Pressure builds gradually, and the ice above maintains the equilibrium, preventing the gas from dispersing. The structure of the ice and sediment, combined with low temperatures and immense overlying weight, has created an extraordinary natural trap. For researchers, these conditions create a puzzle. How stable are these methane pockets, and what events could trigger sudden release? Some isolated zones reveal astonishingly high pressure, suggesting that enormous pockets of methane have been trapped for centuries without detection. These pressure points, measured through careful borehole probes, occasionally rival those found in permafrost regions known for explosive potential. The discovery is particularly puzzling because the locations do not correspond with obvious sources or geological anomalies. Scientists must consider the combined effects of ice flow, subglacial water channels, and sediment composition to explain why these zones have remained intact. Each new reading adds both fascination and unease, indicating that the ice may conceal far more energy than previously realized. The influence of these hidden gases on the ice sheet's movement and stability remains uncertain, raising questions about forces at work beneath the surface. Even minor releases of methane could lubricate subglacial layers, subtly altering flow patterns or accelerating localized melting. Such changes could ripple outward, affecting crevasse formation and the overall dynamics of Greenland's glaciers. While models attempt to account for these variables, the behavior of trapped methane introduces unpredictable elements that cannot yet be quantified. Researchers emphasize caution, noting that what appears stable today may be far less secure under shifts in temperature or pressure. Remote sensing instruments and drilling probes have only begun to reveal these chambers, leaving most of their expanse shrouded in mystery. Satellites detect subtle gas signatures, but the ice's density and depth obscure a precise map of methane distribution. Borehole measurements provide localized data, yet extrapolating this to the scale of the ice sheet is fraught with uncertainty. The combination of inaccessible terrain, extreme cold, and technical limitations ensures that large portions of these gas reservoirs remain beyond observation. Every new method uncovers additional complexity, suggesting that the ice conceals a far richer and more intricate chemical network than anticipated. Seasonal meltwater and subtle warming cycles appear to shift gas pressure, sometimes triggering localized movements or minor releases that elude detection. During warmer periods, thin layers of meltwater may seep into the subglacial environment, slightly altering pressure balances and potentially opening pathways for gas migration. These changes are often imperceptible, yet may accumulate over time, setting the stage for sudden shifts in otherwise stable methane pockets. Monitoring these interactions requires high-frequency sampling and advanced instrumentation, as the subtle dynamics are easily masked by the vastness and opacity of the ice. Comparing Greenland's methane deposits with Siberian permafrost and Antarctic subglacial lakes highlights the region's anomalous patterns, challenging existing geophysical models. While other polar regions show predictable methane behavior linked to temperature and organic content, Greenland displays concentrations that defy such expectations. Some pockets appear ancient, predating the last glacial maximum, while others seem to have formed more recently under unusual conditions. These contrasts suggest that the ice sheet is influenced by a combination of historical, geological, and hydrological factors that remain poorly understood, making Greenland a unique laboratory for studying trapped gases and their potential impact. Researchers debate whether the gas originates from ancient organic matter or deep geological processes, yet no theory fully accounts for its unusual concentration. Some studies indicate that methane could be generated by microbial activity within subglacial sediments, though extreme cold and pressure make such processes slow. Others point to hydrocarbon-rich rock layers beneath the ice, suggesting geologically sourced gas that migrated upward. Both hypotheses have supporting evidence, but neither explains the full scope of what has been measured. The uncertainty emphasizes how little is truly known about the ice's internal chemistry and the forces quietly at work within it. Hidden forces, including minor geothermal gradients and unobserved water flow, may occasionally destabilize these methane pockets, creating phenomena that remain largely unexplained. Even small temperature differentials at the ice base could increase gas mobility, while subglacial streams could erode sediment barriers, subtly altering pressure regimes. These processes might remain undetected until they produce measurable effects, such as localized ice fracturing or micro-releases of methane. The interplay of multiple, largely invisible factors suggests a system in which predictability is limited and surprises may be inevitable, underscoring the profound complexity of Greenland's frozen underworld. Even with advanced monitoring, the full extent and behavior of these gas reservoirs remain elusive, revealing a landscape of frozen complexity far beyond current understanding. New satellite observations, ice-penetrating radar, and borehole sampling continue to uncover anomalies, yet every discovery deepens the sense of mystery. Methane's presence is not just a chemical curiosity, it hints at dynamic hidden processes shaping ice stability, subglacial water flow, and potentially even regional climate effects. Scientists approach each dataset with caution, aware that apparent stability could mask forces that are subtle, ancient, and potentially immense in scale. The ongoing investigation into these methane deposits highlights the unknown nature of Greenland's ice and the challenges of predicting its behavior. With each expedition, researchers refine models but simultaneously confront new uncertainties. The interplay between frozen sediments, trapped gas, and ice dynamics remains poorly understood, a puzzle whose solution may require decades of observation. What is certain is that the ice is not inert. It is a repository of hidden energy, quietly influencing both its own structure and the world above it. A hidden pressure stirs within the trapped methane, suggesting forces and consequences that remain entirely beyond human observation. The mysterious blood snow phenomenon. A vivid red dusts the glacial surface, startling researchers who had long assumed snow in Greenland could only reflect the pale light of the sun. The colour is unnerving, almost theatrical, cutting across the unbroken white in irregular patches that shift with the slope and meltwater flow. Field teams have described stepping onto what seems ordinary snow only to find their boots stained with a faint, persistent crimson, raising questions about its origin and its sudden emergence. Early reports were often dismissed as reflections or sediment, but modern analysis confirms something far stranger is occurring within the ice itself. Centuries of explorers' notes describe similar unusual coloration, yet their accounts offer no real explanation, leaving a record of observations that now feels eerily prescient. Descriptions from the 18th and 19th centuries mention red snow appearing on glaciers where travellers had seen only pristine ice, sometimes spanning hundreds of meters. These historical records suggest the phenomenon is neither new nor isolated, though the frequency and intensity seem to be increasing in the present climate. The gap between recorded observations and scientific understanding underscores a persistent enigma. Why does snow turn red, and what governs its timing and spread? Laboratory analyses of snow samples collected from these crimson patches reveal microscopic algae living within the ice, tiny organisms capable of producing the pigments that stain the snow. These algae, often dormant for months under frozen conditions, can suddenly bloom when surface conditions become favourable. Scientists note that while the organisms themselves are well known, the scale and rapidity of their blooms in Greenland remain difficult to predict. Entire valleys may be coated in red within days, an almost unnatural transformation that confounds conventional models of microbial growth in polar environments. Delicate shifts in temperature, sunlight, and surface moisture appear to create the conditions for these blooms, yet no single variable fully accounts for the phenomenon. Slight increases in solar radiation can trigger photosynthesis in these hardy algae, but some red patches emerge during periods of relatively low sunlight, suggesting additional hidden factors at play. Snow density, microcracks in the ice, and the presence of meltwater channels may all contribute, yet the complexity of these interactions defies precise measurement. Each outbreak seems to have its own rhythm, unpredictable and almost deliberate, as if the ice itself participates in an unspoken choreography. The pigments themselves are more than cosmetic. They absorb more sunlight than ordinary snow, subtly accelerating localized melting. In some areas, red patches appear to deepen depressions in the snow surface, creating miniature channels that guide meltwater and influence microtopography. This feedback loop between biological activity and physical change adds an extra layer of mystery. The algae do not simply colour the snow, they alter it. For glaciologists, these interactions complicate predictions about ice stability and runoff, raising questions about the broader consequences of what was once dismissed as a minor curiosity. Remote imaging has detected extensive red swaths stretching across ice fields, sometimes unnoticed until satellites provide a full view. From orbit, the crimson appears as fleeting streaks or blotches, often in patterns too vast or irregular to be explained solely by wind deposition or mineral dust. Analysts compare these images across seasons, noting that some areas consistently host blooms while others remain untouched. The spatial pattern suggests that localized conditions, perhaps including subsurface nutrients or hidden water flows, are critical to the algae's sudden proliferation, though the exact mechanisms remain elusive. Some valleys repeatedly experience these outbreaks, while nearby slopes remain untouched, hinting at an unpredictable interplay of environmental and biological forces. The selective distribution challenges assumptions about uniform glacial conditions, revealing that even apparently static ice harbours zones of unique activity. Researchers have hypothesized that microclimates, slight variations in snow density, and subsurface heat flux may all play a role, but field measurements are difficult and often yield contradictory results. Each crimson patch thus becomes a case study in complexity, illustrating how life and physics converge in the frozen world. The presence of these algae may also influence local microbial communities and chemical processes within meltwater streams. When red snow melts, it introduces pigments, nutrients, and organic matter into the water, subtly affecting microbial activity and chemical balances downstream. While the immediate effects appear minor, long-term implications for glacial ecosystems are not fully understood. Observers have noted slight shifts in water colour, chemical composition, and even microbial diversity in regions where red snow consistently appears, raising questions about the hidden connections between ice, life, and flowing water. Debate continues among researchers about the precise triggers and origins of the phenomenon. Some suggest that mineral dust or airborne spores could contribute to the pigmentation, while others focus on chemical interactions within the snowpack. A few propose that undiscovered glacial processes, perhaps linked to pressure changes, microfractures, or subsurface melting, play a role. Despite years of study, the phenomenon resists definitive classification, and each new observation seems to open as many questions as it answers, leaving Greenland's crimson snow patches as enigmatic as ever. Recent observations report that the red blooms are appearing in unexpected locations, or earlier in the season than previously recorded, defying existing models of microbial and glacial behaviour. The anomaly has led some scientists to reconsider assumptions about ice sheet homogeneity and the influence of climate change on microbial dynamics. With warmer temperatures and changing snow patterns, plumes may become more frequent or even more intense, though predicting their occurrence remains beyond current scientific capability. The timing, placement and scale of these patches continue to hint at forces operating just out of reach of human measurement. Each crimson bloom challenges assumptions about the seemingly inert ice sheet, revealing a subtle interplay of life, light, and physical processes that is not yet fully understood. The snow's red tint is fleeting, disappearing as temperatures fluctuate and sunlight changes, yet the record it leaves behind, stains on ice, altered melt patterns, and traces in the meltwater, serves as a persistent reminder that the ice is not lifeless. Researchers continue to document these occurrences, but the combination of biological, chemical, and physical factors ensures that the phenomenon retains a sense of unresolved mystery. As the crimson fades from sight, it leaves behind a question that no instrument or theory has yet been able to answer. The strange heat, rising from deep underground. Beneath the vast icy expanse of Greenland, scientists have discovered a phenomenon that has left glaciologists both intrigued and unsettled. Pockets of unusually high geothermal heat rising from deep underground, subtly melting the ice sheet from below. While surface melting driven by climate warming is well documented, the hidden warmth emerging from the bedrock suggests a more enigmatic force at work, one that could reshape our understanding of the ice sheet's stability. Evidence collected from deep boreholes and satellite observations has revealed temperature anomalies that cannot be explained by surface conditions alone, hinting at an internal engine within the frozen continent. Researchers studying the Greenland ice sheet have relied on radar and seismic surveys to probe the interface between ice and bedrock, uncovering patterns that defy conventional models of glacial motion. Certain regions exhibit accelerated basal melting without any obvious surface triggers, and the ice appears to be lubricated in ways that accelerate its flow toward the sea. Scientists have speculated that this underground heat might be concentrated along ancient tectonic faults or geothermal hotspots, but the precise distribution and intensity remain largely unknown. The scale of these anomalies has raised questions about whether our models of glacial dynamics are missing a critical subterranean component. Direct measurements have offered glimpses into the mystery. In 2017, researchers drilling into central Greenland recorded temperature gradients hundreds of meters below the surface that exceeded expected values by several degrees Celsius. Such measurements, while localized, suggest that heat from the Earth's interior may be seeping upward in unpredictable patterns. Unlike volcanic regions, Greenland has no known active volcanoes, making the source of this warmth puzzling. Even more confounding is the irregularity of these geothermal signals, with some areas exhibiting pronounced heating while neighbouring regions remain unaffected. Satellite data has further complicated the picture. Observations from missions such as NASA's Ice, Cloud and Land Elevation Satellite 2, IceSat-2, show subtle changes in ice thickness that cannot be entirely attributed to atmospheric warming or seasonal cycles. When analysed alongside subglacial topography, these anomalies appear correlated with underlying bedrock features, hinting that the warmth might follow the contours of the landscape, rising through ancient channels or pockets within the rock. Such findings have prompted a reassessment of how the ice sheet responds to internal as well as external forces. Glaciologists have also turned to numerical modelling to explore the implications of basal heat. Simulations suggest that localised geothermal flux could significantly increase the velocity of ice streams, causing sections of the ice sheet to move more rapidly than anticipated. In some models, this deep warmth can initiate feedback loops, where melting at the base increases lubrication, which accelerates flow, generating frictional heat that further intensifies melting. These results, while still preliminary, reveal a complexity beneath the ice that challenges the assumption of a static and predictable Greenland ice sheet. Investigations into the bedrock itself offer hints about potential sources. Greenland sits atop a craton of ancient stable rock, yet geophysical surveys have identified regions of thinner crust and residual mantle activity. Some studies suggest that hotspots from Earth's deep interior may intermittently transmit heat upward, concentrating in isolated zones beneath the ice. These geological features could explain why certain areas exhibit higher basal temperatures while others, seemingly nearby, show no signs of warming. The contrast between these regions underscores the enigmatic nature of geothermal heat in an environment otherwise dominated by ice. The influence of geothermal warmth is not merely academic, it has tangible effects on glacial behaviour and ice sheet evolution. Subglacial lakes and channels, formed or sustained by basal melting, alter the distribution of stress within the ice, affecting fracture patterns and calving rates at the edges of the sheet. Scientists have discovered networks of hidden water beneath Greenland, some stretching tens of kilometres, which flow in ways that appear directed by these mysterious heat sources. The discovery of such systems has prompted debates about the potential for sudden, unexplained shifts in ice sheet dynamics. Evidence from isotopic analysis of meltwater offers additional clues. Water collected from subglacial outflows often contains chemical signatures indicative of long contact with bedrock, suggesting slow, deep circulation possibly influenced by geothermal activity. These findings hint at processes operating over geological timescales, where heat from the Earth's interior slowly sculpts the interface between ice and rock. Such subterranean interactions, largely invisible at the surface, may quietly dictate the behaviour of vast glacial systems, producing effects only discernible through careful scientific inquiry. Field expeditions into Greenland's interior reveal the logistical and observational challenges inherent in studying this phenomenon. Extreme cold, crevasse-filled terrain and unpredictable weather limit the placement of instruments and the duration of data collection, leaving many questions unanswered. Yet even limited observations have repeatedly indicated that basal temperatures vary in unexpected ways, with some regions of the ice sheet melting from below despite surface temperatures remaining below freezing. These inconsistencies emphasize how little is truly known about the forces quietly reshaping the Greenland ice sheet from within. Recent studies have also explored the potential implications for global sea level rise. While surface melting remains the dominant contributor, basal heat could subtly accelerate ice flow into the ocean, raising questions about future projections. Because this geothermal activity is largely unmeasured, its full impact remains speculative. Yet the possibility that Greenland's ice could respond from below as well as above introduces a layer of uncertainty into climate models. Scientists caution that ignoring the deep warmth beneath the ice might underestimate the ice sheet's potential for sudden, unforeseen change. As researchers continue to probe the hidden mechanisms driving Greenland's glaciers, the interplay of ice, rock, and heat emerges as a field both tantalizing and opaque. Every new borehole drilled, every satellite observation analysed, seems to uncover further layers of complexity, hinting at processes that are simultaneously ancient and active. The strange heat rising from deep underground remains an enigma that challenges assumptions, blending the solidity of ice with the unseen energy of Earth's interior. The ice conceals secrets that not even centuries of observation can fully illuminate. The unexpected reappearance of ancient viruses. Time itself seems to have been suspended within Greenland, where ancient viruses have re-emerged from ice cores in a state that has left scientists both fascinated and unsettled, challenging assumptions about how long microbial life can survive in stasis. Unlike ordinary pathogens, these viral particles have endured tens of thousands of years, locked away in a frozen archive, silently chronicling a world that existed long before modern humans walked the planet, and offering a window into ecosystems that have long since vanished beneath layers of ice and snow, waiting for discovery by modern science. Each ice core extracted from drilling sites functions as a layered record of Greenland's climate history, yet interwoven within these frozen chronicles are traces of microbial life, dust, pollen, and chemical signatures, all preserved in extraordinary detail. Scientists meticulously examine every centimetre, noting subtle variations in composition, density, and coloration, seeking not only climatic information, but evidence of organisms that survived in ancient, now extinct ecosystems, whose presence may challenge current understanding of microbial longevity and adaptation in extreme polar environments. Some viral fragments have been dated to more than 30,000 years ago, with delicate protein structures remarkably intact, maintained in stasis by sub-zero temperatures, low radiation, and chemical stability within the ice. This preservation defies prior assumptions that microbial life inevitably decays over millennia, and it suggests a resilience of life forms under extreme conditions that is still poorly understood. The very existence of these ancient viruses forces scientists to reconsider the boundaries of biological survival across geological timescales and the mechanisms by which life can remain dormant yet viable for eons. Laboratory studies have revealed that certain viral particles retain the capacity to interact with host cells, an unexpected discovery that hints at dormant functionality and potential biological activity despite tens of thousands of years in stasis. While many microorganisms naturally degrade over time, these viruses demonstrate a persistence that challenges existing models of viral dormancy, prompting questions about whether they could resume activity under the right conditions and what this means for the limits of survival for pathogens previously thought extinct. The implications of such preservation extend beyond curiosity. They raise questions about the evolution of pathogens and the long-term history of microbial life on Earth. Genetic analysis of these viral remnants provides a unique record of viral lineages, potentially illuminating traits that were lost in modern strains and offering insights into past environmental pressures. Ancient viruses serve as a biological archive, revealing evolutionary adaptations and resilience strategies that may have allowed them to survive ice ages, extreme cold, and periods of dramatic planetary change. Warming trends in Greenland have begun to melt some ice layers, suggesting that viruses long confined to frozen chambers could slowly enter active ecosystems. Surface meltwater pathways, seasonal thawing and crevasse channels provide subtle conduits by which these microorganisms may emerge, prompting scientists to consider how such releases could interact with contemporary life. While the risk remains largely theoretical, the notion that these viral remnants may traverse from a frozen past into a living present imbues each discovery with both scientific significance and a quiet, lingering unease. Researchers approach every sample with extraordinary caution, using high-containment laboratories and rigorous protocols to prevent contamination or accidental exposure. Each specimen is handled under strict biosafety level conditions, monitored continuously for activity, and meticulously documented, reflecting both the scientific value of these ancient viruses and the inherent dangers of working with unknown biological material. This careful methodology underscores the delicate balance between exploring long-lost life and safeguarding modern ecosystems from inadvertent exposure. Comparable studies in Siberia and Alaska have yielded viable microorganisms from permafrost, but Greenland's ice cores reveal a scope and diversity previously unseen. These findings suggest that the frozen continent acts as a vast repository of ancient life, offering a singular opportunity to study microbial evolution over tens of thousands of years. Researchers are still mapping the extent of this frozen microbial diversity, and each core drilled adds pieces to a puzzle that spans epochs, ecosystems, and the evolution of life under extreme isolated conditions. The deeper mystery lies in the unknown quantity and variety of viruses still trapped within the ice, silent witnesses to climate cycles, glacial shifts, and biological history. The possibility that hundreds or thousands of viral strains remain hidden, each with genetic information lost to time, introduces profound uncertainty. Scientists can only infer presence from ice layers, chemical markers, and microscopic remnants, yet the true scale of this frozen archive may forever remain partially inaccessible, preserved in the deep and remote reaches of Greenland's icy interior. Scientific debate continues regarding the significance of these ancient viruses. Some researchers emphasize their potential to illuminate evolutionary biology, genetics, and pathogen history, providing invaluable insights into how life adapts and persists. Others caution that the thawing of previously stable ice could inadvertently release microorganisms into contemporary ecosystems, raising questions about pathogenicity, ecological impact, and the unpredictable interactions between ancient and modern life. The tension between discovery and precaution frames much of this research, highlighting the delicate ethics of exploring unknown ancient organisms. Every ice sample tells a story of endurance and resilience, a testament to life's persistence across epochs. Viruses trapped in Greenland's ice are not merely relics, they are reminders of the persistence of biological systems under extreme conditions and the vast unknowns that remain hidden within our planet's frozen landscapes. Their study offers both knowledge and humility, demonstrating that even the most extreme and isolated environments harbour secrets that challenge modern understanding and scientific models. The presence of these viral particles in ice layers spanning millennia underscores the intricate connections between climate, microbial life, and the Earth's history. As scientists extract, analyse, and interpret these cores, they navigate a landscape of frozen time, tracing paths of survival and adaptation that have persisted despite eons of environmental change. Each discovery deepens both our understanding and our questions, revealing that Greenland is not simply a frozen wasteland, but a repository of life waiting to tell its story. This silent archive, preserved through ice ages and climatic upheaval, may yet contain viruses and microorganisms that science has never encountered, each one a vestige of a distant world now hidden beneath layers of frozen history. As warming trends continue, and ice layers slowly yield their secrets, the intersection of past and present becomes tangible, raising questions about the continuity of life, evolution, and the potential for ancient biological forms to re-emerge in ways humanity has never witnessed. Somewhere within Greenland's frozen expanse, the next ancient virus waits, its awakening a question no one can yet answer. The glacier that suddenly stopped retreating. Against a backdrop of steadily shrinking ice across Greenland, one glacier has defied expectations, halting its retreat in a phenomenon that has left glaciologists puzzled and observers questioning the predictability of ice behaviour. The enormous mass of frozen water stretches across fjords and valleys, its surface etched with deep crevasses and seracs, yet it remains curiously stable, as though frozen in time. While other glaciers in the region continue their inexorable march toward the ocean, this anomaly draws attention from researchers, who are determined to understand whether hidden forces or unique local conditions are responsible for its sudden pause. Historical records, aerial surveys, and decades of satellite imagery reveal that most glaciers in Greenland have been retreating at accelerated rates due to rising temperatures and increased surface melting. The patterns are well documented. Ice thins, calves, and flows toward the sea in a relentless rhythm consistent with climate predictions. Against this backdrop of widespread retreat, the glacier's sudden standstill becomes all the more remarkable. Researchers examine long-term datasets, comparing ice flow rates and surface elevation changes, and find that this glacier's motion deviates from every expected trajectory, standing in stark contrast to the relentless pace of its neighbours. Field expeditions and remote sensing data provide detailed observations of subtle advances along certain sections of the glacier, revealing areas where ice seems almost suspended in mid-flow. Crevasses do not deepen, the surface remains remarkably uniform, and meltwater channels appear stable, suggesting a pause that is not merely seasonal, but sustained over multiple years. Satellite radar imagery further confirms the anomaly, showing minimal displacement where flow would normally accelerate. The glacier's behaviour conveys a sense of stillness unusual for such a massive moving body, evoking both scientific curiosity and a quiet tension about the unknown processes at work. The surrounding landscape contributes complexity to the glacier's motion. Fjords, steep mountains, and lateral ice streams create channels that can influence the flow of ice in multiple ways. Despite this, the observed stabilisation cannot be fully explained by topography alone. Adjacent glaciers navigating similar terrain continue to retreat and thin at expected rates, indicating that environmental factors such as slope, valley shape, or lateral confinement may contribute partially, but do not account for the full anomaly. The contrast between the glacier and its neighbours underscores the peculiar nature of its halted retreat. Beneath the glacier, the bedrock is uneven, featuring ridges, basins, and channels that can modulate ice flow. Subglacial topography is known to affect movement, as valleys can trap ice or create frictional resistance, and low points may channel subglacial water that lubricates the base. However, measurements of ice thickness and bed conditions suggest that these features alone are insufficient to explain the sudden stabilisation. The glacier's interaction with its underlying geology remains a critical piece of the puzzle, a hidden influence that continues to elude definitive scientific interpretation. Glacial mechanics further complicate the mystery. Ice flow is determined by basal friction, ice thickness, temperature, and meltwater lubrication. In theory, these factors would lead to continued retreat under current warming trends. Yet this glacier demonstrates that predictable physics can be disrupted by unknown variables or combinations of conditions not yet fully captured in models. Basal ice may freeze in patches, subglacial water may be unevenly distributed, and the internal structure of the glacier may shift subtly to resist motion, creating a complex system that challenges the simplest explanations. Neighbouring glaciers provide a stark contrast. Many continue to accelerate toward the sea, thinning rapidly and calving frequently in response to rising air and water temperatures. Their behaviour is consistent with climate-driven expectations, reinforcing the anomaly represented by the glacier in question. Scientists compare flow rates, surface elevations, and calving frequency, documenting the divergence with precision. The difference highlights that, even within the same region and similar climatic conditions, glaciers can behave unpredictably, suggesting that localized or internal processes may dominate over broader environmental trends in determining ice dynamics. Climate models also struggle to account for this stabilization. Temperature records, precipitation data, and meltwater runoff would predict further retreat, yet the glacier resists these forces. Models calibrated on neighbouring glaciers fail to reproduce the observed behaviour, revealing gaps in the understanding of how ice sheets respond to environmental change. Researchers must reconsider assumptions about glacier-environment interactions, acknowledging that even sophisticated simulations cannot fully capture the nuances of real-world ice movement when faced with anomalies that defy established patterns. Several scientific hypotheses attempt to explain the pause. Subglacial hydrology may be redistributing water in a manner that increases friction. The ice's composition may vary in ways that enhance stability, or geothermal activity could be influencing basal conditions. Each theory offers partial insights, yet none provides a complete explanation. The interplay of multiple factors, ice structure, bedrock geometry, water pressure, and temperature gradients, likely contributes to the phenomenon, yet the exact combination remains unknown. This multiplicity of possibilities preserves the mystery, inviting further investigation into processes that operate on scales and in ways not yet fully understood. The unexpected stabilization carries implications for forecasting and planning. If glaciers can halt or advance unpredictably, projections of sea level rise may need re-evaluation, and assumptions about ice sheet responsiveness to warming may be too simplistic. Scientists must factor in unknown or poorly understood processes when modelling Greenland's contribution to global sea levels. The anomaly serves as a cautionary example of the limits of predictive power in glaciology, reminding researchers that even large-scale, slow-moving systems can behave in ways that defy the best scientific expectations. Research efforts face formidable challenges. Remote locations, harsh weather, and treacherous ice surfaces make repeated field measurements difficult. Equipment can fail, and access is often restricted to brief seasonal windows. Consequently, continuous data are sparse, leaving gaps in understanding. Scientists rely heavily on satellite observations and aerial surveys, yet these tools cannot capture every nuance of subglacial conditions or internal ice dynamics. The logistical difficulties of studying Greenland's ice sheets magnify the sense of mystery surrounding the glacier's halted retreat and underscore the limits of human observation in extreme environments. The glacier's behaviour offers a broader perspective on nature's unpredictability. Even colossal ice bodies, measured in kilometres and centuries, are subject to forces and interactions that remain only partially understood. The stillness observed is not merely a scientific curiosity, it is a reminder that natural systems possess complexity beyond human anticipation. Each frozen ridge and subtle crevasse reflects processes operating across spatial and temporal scales that challenge direct measurement and simple interpretation, emphasizing the enduring tension between observation and understanding in polar science. While nearby ice streams continue their relentless descent toward the ocean, this glacier's sudden pause embodies a paradox: immense, powerful, and yet curiously inert, as though defying the very climate and physics that drive its neighbours. Its unexpected stabilization invites reflection on the forces, both visible and hidden, that govern Greenland's ice sheets. The phenomenon reminds researchers that even in an age of advanced technology and modelling, the natural world retains the capacity to surprise, resist, and preserve secrets that human science has yet to unravel. Whatever hidden dynamics sustain its pause, the glacier's silent endurance leaves a lingering question about the limits of human understanding and the secrets still locked within the frozen continent. The mysterious subglacial sediment plumes. Clouds of sediment surge into the icy fjords, carried by unseen currents that rise from the glacier with a suddenness that defies prediction. These ephemeral flows appear almost like smoke beneath the water, twisting and coiling as they ascend, carrying minerals and traces of organic matter scraped from the bedrock far below. Observers on nearby vessels or monitoring via sonar can only capture fragments of their forms before they dissipate into the fjord, leaving behind a faint discoloration in the water. Despite decades of monitoring, the scale and suddenness of these surges continue to puzzle those attempting to understand Greenland's hidden glacial dynamics. Sonar readings, submersibles, and water sampling reveal only fleeting glimpses of the plumes, capturing their dynamic forms in partial snapshots that vanish almost as quickly as they appear. Each expedition provides small pieces of a larger puzzle, yet no single observation captures the full rhythm of their emergence. The plumes can vary dramatically from one site to another, with some rising in dense, narrow columns while others spread broadly across the fjord in ghostly sheets. The behaviour appears irregular, both in timing and intensity, suggesting forces beneath the ice that are both powerful and highly localised, yet remain largely invisible to human measurement. Fine mineral particles and traces of organic matter swirl together, forming patterns that suggest processes far more powerful and complex than surface melt alone could explain. Tiny rock flour and clay-sized sediments, mixed with detritus from long-buried plant matter, create a heterogeneous composition that hints at violent scraping along the glacier bed. The sediment's distribution often defies simple expectations, rising rapidly in concentrated bursts before settling unevenly across the fjord. The variety and density of these materials reveal that the glacier's basal zone is not uniform, but a shifting mosaic of pressure, friction, and occasional subglacial flooding, making each plume a unique fingerprint of the processes occurring below. As they ascend, these plumes twist and fan unpredictably, sometimes creating dense columns, sometimes diffusing into thin, ghostly sheets that disappear within hours. Water currents, temperature gradients, and the interaction with incoming seawater all shape the plume's paths, adding layers of unpredictability. Observers note that even slight changes in tide or wind can affect the dispersal, and no two events are alike. The ephemeral nature of these surges underscores the challenge of interpreting them. Each momentary formation carries clues about forces operating in darkness, yet the patterns remain transient and teasingly elusive. Hidden channels carved by meltwater guide the sediment along intricate paths, yet even detailed mapping cannot fully account for the bursts and surges observed beneath the ice. Subglacial rivers, sometimes tens of meters wide, funnel both water and sediment, yet the timing and volume of the resulting plumes vary dramatically. In some cases, plumes appear suddenly without an apparent trigger, suggesting episodic surges or sudden release from pressure pockets trapped beneath the ice. The landscape beneath the glacier is complex, a network of pathways and cavities that direct the flow of material. But the mechanisms that produce these rapid, intermittent discharges remain poorly understood. Fluctuations in density and movement provide indirect evidence of glacial mechanics, hinting at pressures, friction, and melting occurring out of sight and beyond direct measurement. Denser, faster-moving plumes may indicate sudden basal melt or localized increases in water pressure, while lighter, more diffuse clouds suggest slower release or mixing with ambient water. These observations reveal the glacier's activity as a hidden dance of forces, where small changes beneath the ice can produce visible, sometimes dramatic, effects at the surface. Even without direct observation, the plumes act as messengers from a world largely concealed from view. Neighbouring ice streams offer contrast, flowing steadily into the ocean, yet none produce plumes of comparable scale or sudden intensity, emphasizing the anomaly's peculiarity. While other glaciers release sediment gradually and predictably, these surges occur with an irregularity that confounds conventional models of ice and meltwater behavior. The discrepancy demonstrates that Greenland's glaciers cannot be treated as uniform systems, and that subglacial processes can vary widely, even across a small geographic area. Each plume becomes a signal, an unexpected and fleeting indicator of forces operating where direct measurement is impossible. Once these clouds reach the fjords, They alter salinity, deliver nutrients, and temporarily reshape ecosystems, revealing the far-reaching impact of events hidden deep within the ice. Fish and microbial life respond to the influx of fresh water and mineral content, and plankton blooms can emerge in the wake of the plumes. The sudden addition of material changes the chemical and physical properties of the fjord, creating a brief but significant shift in local environmental conditions. Even these surface effects, observable by monitoring equipment and local observers, remain only indirect evidence of the immense hidden activity that produced them. Several possible explanations arise: episodic subglacial floods, unusual erosion patterns, or geothermal influence, yet none fully account for the plume's irregular emergence. Hypotheses suggest that water trapped beneath the glacier may suddenly release, scouring channels and lifting sediment in pulses that reach the fjord. Bedrock composition and localized friction could amplify or modulate these surges, but current knowledge cannot definitively link cause and effect. Even the most sophisticated models struggle to reproduce the observed variety and timing, leaving each plume a mysterious event that teases at deeper unseen processes. Observation remains difficult. Icebergs, fast currents, and extreme temperatures limit access, leaving only fragments of evidence and tantalizing hints to piece together. Field teams face unstable surfaces, rapidly shifting water, and short seasonal windows, often relying on remote sensing to supplement sparse in-person measurements. The limitations of direct observation mean that each plume is studied more as a fleeting impression than as a fully documented phenomenon, reinforcing the sense that the glacier's hidden world is active and complex, yet largely beyond human control or understanding. Sediment layers carry a hidden history, hinting that past ice flows and melt events have left subtle signatures transported upward by these mysterious plumes. The composition of particles can indicate the types of rock encountered, the depth of glacial movement, and the forces exerted at the icebed interface over centuries. By examining repeated surges over time, patterns emerge that link present observations to long-term glacier behavior, suggesting that these ephemeral clouds are not random, but echoes of processes operating at scales too slow or concealed for direct measurement. Each new surge reminds us that the glacier conceals a complex and largely invisible system, where water and rock interact in ways still poorly understood. Plumes can vary within hours, influenced by changes in pressure, subglacial topography, or localized melting, demonstrating that the glacier's base is a dynamic and unpredictable environment. Observers watching the rise and dispersal of sediment witness only a fraction of the processes, yet even these brief glimpses reveal that vast energies and forces are at work beneath the ice, shaping both the glacier itself and the surrounding fjord. The swirling sediment offers a fleeting glimpse of forces operating under immense pressure, hinting at processes that remain inaccessible to direct human observation. Each pulse provides evidence of sudden movement, material transport, and subglacial dynamics, yet its irregularity preserves the mystery of what triggers the bursts and how the forces interact within the ice. Each plume rises and dissolves like a whispered secret, leaving the fjords to carry away evidence of a hidden world that refuses to reveal its full story. The massive ice caverns hidden inside the glacier. Enormous hollow spaces carved entirely from ice stretch silently beneath Greenland's glacier, forming caverns whose scale and stability continue to perplex experts despite modern mapping techniques. These chambers extend for hundreds of meters in length, with ceilings that rise in sweeping arcs and walls etched by centuries of glacial movement. The formations appear at once natural and monumental, as if shaped by some subterranean artistry. Remote sensing equipment reveals that the ice holds tension and memory, storing evidence of slow shifts, melting pulses, and basal pressures that collectively maintain these vast empty spaces in near-perfect balance. Ground-penetrating radar and ice-penetrating lidar scans have uncovered passages so expansive that explorers can walk for minutes beneath the glacier without sighting a wall, the ceilings arching above like frozen cathedrals. Mapping attempts capture only fragments, revealing irregular chambers connected by winding tunnels and hidden recesses that resist straightforward measurement. Even when lighting equipment illuminates the interior, shadows stretch endlessly, emphasizing the enormity and complexity of these underground voids. The combination of light and ice creates a surreal environment where reflections and refractions distort perception, making navigation both mesmerizing and precarious. Inside these halls, ice pillars rise from floor to ceiling, some wide and solid, others delicate as glass, forming natural sculptures that seem both ornamental and structural. Walls shimmer with layers of trapped air bubbles, glacial striations, and occasional mineral veins, creating textures that shift subtly with changes in light or perspective. The floors are smooth in some areas and rough in others, shaped by centuries of meltwater flow, ice creep, and occasional fracturing. Every surface hints at the glacier's long history and concealed activity, with patterns that both document and mystify. Subglacial physics suggests that these caverns are created by a combination of basal melting, the pressure of overlying ice, and the slow movement of ice layers that stretch and fracture the material. Meltwater channels carve passages and hollow pockets, while ice deformation allows voids to persist without collapsing. Yet even detailed models cannot fully predict why certain caverns maintain stability for decades, while others fail, leaving a gap between theory and observation that adds to their intrigue. Some caverns display sudden drops, twisting corridors, and unexpected expansions that defy simple explanations of ice flow. These irregular shapes suggest hidden subglacial dynamics, perhaps including localized water surges, stress redistribution, or microtopographical variations in the bedrock. The interiors resist conventional interpretation, revealing a level of structural complexity that is difficult to reproduce in laboratory conditions or computer simulations. Each discovery prompts further questions about the processes operating beneath the glacier, and the more that's learned, the deeper the mysteries appear. Air trapped within the ice circulates subtly through these spaces, maintaining temperatures just below freezing and creating a delicate equilibrium. Even slight disturbances, such as a new fracture or pressure shift, can alter airflow and threaten cavern stability. Explorers must move cautiously, aware that the crystalline ice is both breathtaking and brittle. The combination of visual grandeur and environmental fragility makes every expedition into these halls an exercise in both awe and precision, highlighting the extreme care required to study such a hidden and volatile system. Visitors often describe an almost tangible silence inside the caverns, broken only by distant creaks, dripping meltwater, or the echo of a footstep. Sound behaves strangely in these vast spaces, bouncing off walls and creating reverberations that emphasize isolation and scale. The sensory experience reinforces the perception of a world apart, where time slows and the human presence feels simultaneously intrusive and infinitesimal. Each journey emphasizes that these ice cathedrals are not only physically imposing but psychologically arresting, evoking both reverence and unease. Seasonal and environmental changes further limit access and study, with thickening ice and unstable surfaces restricting fieldwork to narrow windows. Remote sensing can partially compensate, but much of the cavern network remains uncharted. Each mapping attempt provides tantalizing glimpses, but fails to capture the full complexity of the interconnected spaces. This partial knowledge maintains a sense of ongoing discovery, reminding researchers that the glacier conceals a vast subterranean landscape that cannot be fully documented with current technology. The presence of these massive voids also subtly affects glacier dynamics, altering basal friction and redirecting ice flow in localized regions. Large cavities may relieve pressure, enabling sections of the ice sheet to shift more freely, while smaller voids can concentrate stress and influence melting patterns. Understanding the interaction between caverns and overall ice behavior is crucial for glaciologists attempting to predict long-term glacier movement, yet these hidden structures remain largely invisible, making precise modelling extraordinarily challenging. Compared to ice caves in Antarctica or Iceland, Greenland's caverns are notable for their longevity, scale, and intricate structure. Other glacial chambers may collapse quickly or be restricted to smaller dimensions, but these vast ice halls persist, defying ordinary expectations. Their durability points to unique combinations of ice thickness, temperature regulation, and subglacial water flow that allow them to remain intact over decades or centuries. Even within well-studied regions, new voids continue to be discovered, emphasizing how much of the glacier's interior remains unexplored. Each expedition into these icy interiors uncovers new formations, twisting pillars, layered walls, and echoing passages that highlight the glacier's complexity and the creativity of natural processes. These discoveries demonstrate that the glacier is not a static mass, but a dynamic and hidden landscape, sculpted by forces that act slowly and invisibly over millennia. The experience of navigating these chambers reinforces the sense that Greenland's ice hides monumental features, both fragile and enduring, whose full extent and function are still largely unknown. These hidden cathedrals of ice endure in silent secrecy, guarding forces beneath Greenland's glacier that may never be fully understood. The radar shadows beneath the ice sheet. In certain stretches of Greenland's ice sheet, radar scans reveal vast, unexplained voids where signals vanish entirely, leaving observers staring at blank spaces beneath the glacier. These shadowed regions appear as sudden interruptions in otherwise consistent ice readings, baffling teams who rely on ice-penetrating radar to reveal the terrain below. Flights over the ice reveal a patchwork of echoes and absences, creating maps that are as mysterious as they are precise. Technicians and field scientists note that these blank areas persist across multiple scans, suggesting that they are not artifacts of equipment error, but rather features of a hidden and largely unknown subglacial landscape. Airborne and ground-based surveys capture intricate details of surrounding ice, yet when measurements encounter these shadows, the instruments record nothing, as if the ice itself swallows information. Sophisticated radar arrays designed to detect variations in ice density and subglacial topography repeatedly fail to return usable data in these locations. Analysts have documented patterns in which echoes abruptly vanish, only to reappear meters or kilometers away, forming disjointed or irregular readings. This creates a scenario where scientists must reconcile reliable measurements with complete blind spots, leaving entire swaths of Greenland's subsurface a literal mystery, hidden from direct observation and confounding any attempt to model the area accurately. The anomalies appear suddenly, sometimes spanning kilometers, and behave inconsistently, creating areas where depth, density, and structure cannot be determined through conventional radar methods. In some cases, a region will behave predictably for part of a scan, then abruptly disappear, producing readings that defy explanation. These blank zones are not isolated, but rather emerge in clusters, suggesting a relationship with deeper glacial structures or hydrological channels. Despite years of survey data, the behavior of these shadows remains erratic, making it impossible to produce continuous maps of ice thickness or subglacial terrain in these areas. Every scan reinforces the sense that the glacier conceals features that lie beyond even our most advanced detection technology. Unlike regions of uniform ice that reflect signals predictably, these shadows produce distorted or missing echoes, emphasizing their peculiarity and separating them from any normal subglacial feature. Typical ice layers allow radar waves to penetrate and return clear signals, mapping out ridges, valleys, and subglacial lakes. In contrast, the shadows act almost like voids, where waves fail to return or are scattered unpredictably. These inconsistencies have been observed across multiple expeditions and instruments, indicating that the anomaly is a genuine geological or glaciological phenomenon rather than a technical artifact. The resulting maps reveal a fragmented underworld, one that invites more questions than it answers and underscores the limits of human observation. Scientists have proposed water pockets, dense sediment layers, or unusual ice composition, but none of these explanations account fully for the abrupt and repeating signal losses. Hypotheses include subglacial lakes or tunnels that absorb radar waves, or regions of highly compacted ice interspersed with debris that scatters signals unpredictably. Even the presence of mineral-rich sediments or isolated geothermal effects cannot explain the regularity and recurrence of certain shadows. Each theory provides partial insight, but the precise combination of factors responsible for these radar voids remains elusive. The phenomenon continues to provoke debate, suggesting that the glacier contains features or dynamics that defy straightforward classification. Extreme cold, thick ice, and equipment sensitivity further complicate observation, making it difficult to rule out natural interference while reinforcing the sense of an uncharted hidden zone. Operating instruments in sub-zero conditions demands meticulous calibration, and temperature variations can subtly alter signal propagation. The sheer thickness of the ice sheet, which can exceed several kilometers, adds another layer of complexity, diminishing radar penetration in some areas and intensifying shadow effects in others. Despite these challenges, the patterns persist, suggesting an underlying reality beyond environmental interference. Each expedition into radar analysis becomes a journey into a ghostly space, where the absence of signal is as telling as any echo. Some patterns recur across surveys, hinting at consistent features or structures beneath the ice, yet no direct evidence has confirmed what lies within the radar shadows. Clusters of blank zones align along certain paths, suggesting hidden channels, subglacial depressions, or previously undetected lakes. While their presence hints at structural regularity, the inability to penetrate or visualize them leaves their true nature unknown. This repeating pattern raises questions about how ice sheets conceal complex internal networks and what role these features may play in basal hydrology or ice flow. Each map highlights the ghostly architecture of the glacier, revealing hidden spaces that persist beyond scientific reach. The anomalies could influence glacier flow, basal water channels, or ice sheet dynamics, yet the lack of direct measurement leaves only partial insights into these mysterious voids. If large subglacial cavities exist, they may reduce friction at the icebed interface, subtly accelerating nearby sections. Conversely, hidden sediment layers could impede motion or redirect meltwater, creating unexpected variations in flow patterns. Understanding these potential influences is crucial for predicting the long-term behavior of Greenland's ice sheet, yet the inability to resolve these shadows in detail leaves climate and glaciological models incomplete. The ice conceals not just physical space but dynamic processes that remain invisible and enigmatic. Physical exploration is impossible in most of these areas, so the shadows remain beyond human reach, their secrets preserved by layers of ice and the limits of current technology. Drilling through kilometers of dense ice to reach these zones is impractical, and the potential hazards of unstable ice above any cavity make direct access dangerous. Remote sensing remains the only viable window into these hidden regions, yet it can only provide fragmented glimpses, leaving large portions entirely unexplored. These invisible voids become a symbol of the glacier's secret interior, a realm where human curiosity is limited by the very material we seek to study. The debate continues among glaciologists, some interpreting the voids as natural subglacial formations, others as signals of processes still unknown, yet all acknowledge the puzzle defies easy explanation. Some theorists suggest channels formed by meltwater or glacial deformation, while others speculate about sediment accumulation or variations in ice crystallinity. Despite the variety of models, no consensus has emerged, and each new dataset introduces additional anomalies or inconsistencies. Conferences and papers repeatedly highlight the limits of our current knowledge, reinforcing the idea that Greenland's ice sheet may harbour phenomena entirely beyond current scientific comprehension, patiently concealed beneath its frozen expanse. Each new survey reveals slight changes, unexpected anomalies, and additional shadowed regions, reinforcing the notion that beneath Greenland's frozen surface exists a concealed world resisting full comprehension. Subtle shifts in radar returns suggest that the features are dynamic, evolving, or responding to subglacial processes that remain poorly understood. Observers note that these voids do not behave like static structures, but rather as living components of the glacier's internal system. With every mapping attempt, the shadows grow more complex, and the narrative of the ice sheet transforms into one defined as much by its absences as by its measurable features, leaving the hidden interior tantalizingly elusive. These vanish signals hint at a hidden realm beneath the ice, a domain that challenges both technology and imagination, and whose secrets may never be fully uncovered. The icebergs that suddenly flip without warning. Towering icebergs can suddenly overturn as they detach from Greenland's glaciers, releasing enormous energy in a matter of seconds and leaving experts struggling to predict the event. These flips often occur without visible warning, with the ice shifting violently as it interacts with water currents and tidal forces. Fjords filled with carved ice become stages for these dramatic eruptions, where the movement of a single massive iceberg can send waves and turbulence cascading through the surrounding waters. Observers have documented cases in which nearby ice fragments are displaced, and even well-anchored monitoring equipment is shaken, illustrating the immense power contained in these frozen giants. From satellite imagery, aerial photography, and time-lapse recordings, moments of violent motion are captured, revealing flips that appear almost instantaneous against the frozen landscape. Analysis of these sequences shows how seemingly stable icebergs can suddenly rotate, exposing enormous submerged faces and redistributing mass with catastrophic force. The camera angles reveal the complexity of ice geometry, with submerged keels and overhanging edges interacting in unpredictable ways with both water and neighbouring ice. Each captured event offers a fleeting glimpse into the immense energy stored within these formations, but the rapidity of their overturning ensures that no single survey fully captures the dynamics of each flip. These icebergs often weigh millions of tons, with sheer faces and submerged keels that interact unpredictably with surrounding water, creating a precarious balance that can collapse without warning. The buoyancy of the submerged ice, combined with the force of meltwater channels beneath the glacier, contributes to a tension that can suddenly resolve in violent motion. Even minor fractures or uneven melting can tip the balance, unleashing rotational force that overturns sections of ice, sometimes flipping them entirely. The scale of these events dwarfs small vessels and floating ice, illustrating how the sheer mass of these giants transforms them into forces capable of reshaping their immediate environment in seconds. Calving glaciers frequently produce ice masses that seem stable, only for some to tilt, roll, or spin violently moments later, exposing gaps in our understanding of glacial mechanics. Traditional models of calving behaviour anticipate gradual detachment or controlled fragmentation, yet many flips occur without preceding signs. This unpredictability challenges assumptions about ice stability and raises questions about how internal stresses propagate through massive ice structures. Observed flips demonstrate that icebergs are not static objects, but dynamic systems influenced by hidden variables, such as internal fracturing, meltwater infiltration, or interactions with submerged ice, revealing processes that are often invisible until the moment of catastrophic movement. Evidence suggests that uneven melting, shifting tides, underwater currents, or internal fractures may trigger flips, yet no single factor fully explains why certain icebergs behave this way. Warm surface waters can erode the base of floating ice, subtly shifting weight distribution until a tipping point is reached. Tidal cycles exert pressure from below, sometimes interacting with underwater topography to create sudden rotations. Internal ice fractures, often undetectable until failure, may act as hidden hinges, allowing enormous sections to pivot. Despite these plausible factors, the precise combination that triggers any particular flip remains elusive, leaving each event as a puzzle where cause and effect can be inferred but rarely observed directly. Capturing these events proves difficult, as icebergs can flip in remote fjords or open seas, often far from instruments, making real-time observation nearly impossible. Ships are rarely in the right position to witness a flip safely, and aerial surveys depend on ideal conditions to record the moment. Automated monitoring equipment may only register secondary effects, such as waves or acoustic signatures, providing incomplete data. The vastness of Greenland's coastline, combined with unpredictable ice behaviour, ensures that many flips occur entirely outside human observation, emphasising the hidden and uncontrollable aspects of these phenomena. Each recorded event is therefore both rare and valuable, offering fleeting insight into processes that are otherwise invisible. When an iceberg rolls, it displaces enormous volumes of water, generating waves, turbulent currents, and dangerous conditions for nearby vessels, wildlife, and smaller ice fragments caught in its path. The sudden redistribution of mass can send cascading waves through fjords, capsizing smaller icebergs or disturbing marine habitats. Seals, birds, and fish experience abrupt changes in water pressure and motion, while human-made structures may face unanticipated hazards. The energy released in a single flip can be equivalent to a small earthquake in localized effect, illustrating the scale of forces involved. These dynamics underscore the interconnectedness of ice, water, and life in glacial regions, where a single shift can ripple across multiple systems. Icebergs in Greenland sometimes display unusual frequency or scale compared to other polar regions, hinting at hidden environmental or structural influences beneath the ice. While flips occur globally wherever glaciers carve, Greenland's fjords present a combination of tidal forces, deep water channels, and rapid melting that appears to amplify instability. Observed flips often involve exceptionally large ice masses, suggesting that local conditions may create unique vulnerabilities within the ice. Patterns emerging from recorded events hint at systemic factors influencing iceberg behaviour, yet the precise interplay of water, ice, and glacier structure remains largely speculative. This regional distinctiveness highlights Greenland as both a natural laboratory and a site of ongoing risk and mystery. Experts analysing the flips consider factors ranging from subglacial stress patterns to melt-induced destabilisation, yet the precise triggers remain a puzzle that defies current models. Theoretical simulations attempt to replicate rotations and tilts, accounting for buoyancy, ice density, and water displacement, but real-world events frequently exceed modelled predictions. Each flip provides new anomalies, prompting refinements of glaciological understanding but rarely offering conclusive explanations. The complexity of these systems lies not only in the physical parameters of the ice, but also in interactions with hidden currents, ice fractures, and tidal cycles, ensuring that each event remains both unpredictable and instructive for scientists studying glacier behaviour. Those navigating these waters must contend with sudden eruptions of motion, falling ice, and colossal waves, illustrating how the frozen environment holds dangers that appear without warning. Expedition crews report moments when calm waters transform into chaos within seconds, forcing rapid response to maintain safety. Even experienced crews with advanced instrumentation are vulnerable to the hidden power of tipping icebergs, as the mass and speed of a single flip can overwhelm human reaction. These hazards reinforce the necessity of remote monitoring and distance, emphasizing that while the events are scientifically compelling, they're also inherently perilous to those attempting direct observation. Each new flip observed reinforces the sense that Greenland's glaciers conceal immense forces beneath their frozen surfaces, forces that operate beyond the limits of prediction or modelling. Even with decades of glaciological study, the ice continues to surprise, producing events that challenge assumptions about stability and risk. Detailed recordings, simulations, and anecdotal reports all converge on the notion that beneath the serene white surfaces lies a volatile and dynamic world where hidden stresses can erupt without warning. The unpredictable nature of these flips ensures that the glaciers retain an element of mystery, reminding all who study them that much remains unknown. The violent overturning of these colossal ice masses serves as a stark reminder that beneath Greenland's serene icy exterior lies power that can erupt with no warning. The ancient climate record locked in Greenland's ice cores. Layers of frozen material hold chemical signatures and gas bubbles that chronicle Earth's climate in astonishing detail, revealing sudden shifts that defy conventional explanations. These shifts appear in the cores as abrupt changes in isotopic composition, temperature indicators, and trapped greenhouse gases, signalling periods of rapid warming or cooling that occurred far faster than modern instruments could measure. Researchers analysing these features have documented instances where centuries of relative stability were interrupted by sudden events that remain unexplained. Each section of the core is a meticulous record, with fine layers that can be read like the pages of a book, yet some pages contain enigmatic passages that challenge interpretation. Drilling deep into these compressed layers requires delicate precision, as even minor disruptions can erase centuries of environmental history encoded within the ice. Specialized drills cut through kilometers of ice, often operating in sub-zero temperatures and high winds, while core segments are immediately preserved to prevent contamination. Handling and transport of the cores must maintain exact conditions to retain trapped gases and chemical signatures. Ice cores recovered from depths exceeding 2 kilometers can contain continuous records stretching back hundreds of thousands of years, allowing scientists to reconstruct climate events far beyond the reach of conventional geological records. Air trapped in microscopic bubbles provides a direct sample of ancient atmospheres, showing variations in carbon dioxide, methane, and other greenhouse gases that influenced Earth's climate. These bubbles capture snapshots of conditions at the moment the snow compacted into ice, preserving chemical compositions across eons. By analysing gas concentrations and isotopic ratios, scientists can detect abrupt rises or falls in greenhouse gases, sometimes coinciding with sudden temperature shifts. This frozen atmosphere offers unique insight into the pace and magnitude of ancient climate events, revealing patterns that are often more extreme or rapid than models of gradual change would predict. Certain sections of the cores reveal abrupt temperature swings, rapid transitions that suggest dramatic events occurred far faster than previously assumed. These anomalies can span mere decades, yet appear as distinct layers in the ice, marked by isotopic shifts or changes in crystal structure. The speed and intensity of these swings suggest environmental triggers that remain partially mysterious, including volcanic eruptions, shifts in ocean currents, or other global perturbations. Interpreting these rapid events challenges scientists to reconsider assumptions about climate stability, showing that even long periods of apparent calm could be punctuated by sudden upheaval. Analysis of isotopic ratios, volcanic ash, and mineral fragments embedded in the ice uncovers evidence of storms, eruptions, and unknown phenomena that shaped Earth's climate long before modern records. Layers rich in volcanic ash indicate explosive eruptions that dispersed material globally, while mineral inclusions and dust layers hint at desertification or wind-borne sediment transport from distant continents. These chemical and physical signatures provide context for abrupt climate changes recorded in the ice, allowing researchers to correlate specific events with global impacts. Yet some layers contain anomalies that do not match any known event, leaving their origins a lingering mystery. Some chemical anomalies and dust influxes cannot be linked to documented events, presenting enduring puzzles for scientists attempting to reconstruct the past. Spikes in trace elements or unusual particulate compositions appear in isolated sections, hinting at events or processes not reflected in historical geology or other paleoclimate records. These irregularities may represent localized phenomena, unknown atmospheric disturbances, or previously unrecognized mechanisms capable of influencing climate. Each anomaly challenges the ability to construct a coherent narrative of Earth's past, and serves as a reminder that even the most meticulously recorded archives conceal secrets that science has yet to explain. Even amidst recurring cycles of accumulation and melt, isolated outliers appear, highlighting periods of unpredictable environmental change that challenge existing climate models. Rhythms in snowfall and ice formation are generally consistent, creating a framework of regular layering, yet abrupt deviations punctuate this pattern. These deviations suggest forces that operate beyond the usual climatic drivers, producing sudden and unanticipated results. By studying these outliers, scientists attempt to discern hidden mechanisms within Earth's climate system, though the exact causes often remain elusive, emphasizing that natural variability can be far more complex and volatile than anticipated. Synchronizing these ice records with data from ocean sediments and Antarctic cores reveals both globally mirrored events and unique regional phenomena, deepening the mystery of climatic history. Some abrupt warming or cooling episodes occur simultaneously across hemispheres, suggesting planetary-scale forces, while others remain confined to Greenland, indicating local triggers or interactions. Comparing these datasets allows researchers to differentiate between widespread environmental shifts and regional anomalies, yet the causes of many isolated events remain uncertain. The combination of global synchronicity and localized irregularities reinforces the notion that Earth's climate history is a tapestry woven from both predictable cycles and mysterious disturbances. Trapped within the layers are signs of extreme sensitivity, where small shifts in temperature or chemistry could trigger larger systemic changes, though mechanisms remain partially unknown. Ice cores show that minor variations in greenhouse gas concentrations or dust deposition can coincide with abrupt climate transitions, revealing a system that responds dramatically to relatively small perturbations. Feedback loops involving oceans, atmosphere, and ice amplify these effects, yet not all rapid changes are fully accounted for by known feedback mechanisms. The cores emphasize how delicate the balance of past climate was and how seemingly minor events could cascade into significant environmental consequences. Modern techniques can extract detailed records from the cores, yet each discovery introduces new enigmas that confound scientists' understanding of Earth's past climate behavior. Advanced mass spectrometry, isotopic analysis, and imaging reveal unprecedented detail about chemical composition and layering, but often highlight anomalies that resist conventional explanation. Each new finding forces reconsideration of established theories and suggests that the climate system operated with a complexity that continues to challenge predictive models. The frozen archive is simultaneously a treasure trove of knowledge and a source of profound uncertainty, demonstrating both the power and the limits of paleoclimatic research. Meticulous examination of these frozen archives continually uncovers hidden patterns, yet the deeper the record goes, the more questions arise about the forces that shape them. Some sequences indicate repeated cycles of change, while others contain abrupt, unexplained shifts, creating a juxtaposition of predictability and mystery. Researchers continue to analyze chemical, isotopic, and particulate data, attempting to decode the messages locked in each layer, but the ice retains secrets that resist easy interpretation. The ancient climate record preserves a complex interplay of stability and chaos, offering glimpses into processes that shaped the world long before human observation. Each bubble and particle locked within the ice whispers secrets of a climate long vanished, hinting at